students, welcome to our YouTube channel Raj Academy. The main aim of this lecture is to discuss some of the important points of the electrical machines in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel and don't forget to press the bell icon button. So whenever we upload a new video, the direct information comes from well. If any improvements are needed in our lectures, then please do comment in the comment section. We will definitely improve all those improvements in the coming lectures. So without wasting more time, so let's get started. See, ferromagnetic material has the more magnetic permeability than diamagnetic material. So ferromagnetic material will have the huge amount of permeability when compared to diamagnetic material. So the reluctance of the ferromagnetic material is less than the diamagnetic material, which is the reluctance is inversely proportional to mu. As I already told you in the transformers itself, R is equal to L by mu into A. The reluctance is inversely proportional to magnetic permeability. So more is the magnetic permeability, the less is the reluctance of the core. So we try to use the ferromagnetic materials to make the core because there the ferromagnetic materials has the higher amount of magnetic permeability when compared to diamagnetic material. So its reluctance decreases. So therefore, for a small amount of magnetic for a small amount of magnetic current, we can get the huge amount of flux. That is what we need. That is what we actually need. We need a core of less reluctance and with a less amount of current, we need to have the rated amount of flux in the core. That is our agenda, to keep the maximum flux in the core, which is achieved by ferromagnetic materials. So we prefer to use the ferromagnetic materials to make the transformer core. So therefore we can say that ferromagnetic materials has the more magnetic permeability when compared to diamagnetic material. So therefore the reluctance of the ferromagnetic material is lesser when compared to diamagnetic material, because more is the magnetic permeability, the less is the reluctance of the core. That is the reason we always prefer to use the ferromagnetic material rather than the diamagnetic material to make a core of the transformer. As you can see clearly, as the magnetic permeability increases, the reluctance of the core decreases. So therefore, with a small amount of current, we can get the huge amount of flux in the core. This is our agenda in making the transformer core. So we always choose a material which has the huge amount of magnetic permeability, so its reluctance will be very less. So even for a small amount of magnetizing current, we can get a huge amount of flux in the core. In BH curve, during in linear region, mu is equal to constant, but in saturation region, as I increases, mu decreases and R increases. So let me tell you in detail regarding this point. See, in a BH curve, during in linear region, mu is equal to constant, because in a linear region, B is directly proportional to H. So therefore, what is a mu? Mu is called as the slope of the BH curve. So therefore, mu is equal to B by H, or simply we can say the slope of the BH curve. So under the linear region, the slope is constant. The slope is constant means the magnetic permeability is a constant. But in saturation region, as I increases, a less amount of increase of B is going to happen. See, for a huge amount of increase of I, a small amount of increase of B is going to happen. So therefore we can say slope is equal to B by H. H is directly proportional to I and B is directly proportional to flux. So simply we can say that mu is equal to B by H or phi by I. A very large increase in I will give you a small amount of increase in flux. So phi amount of increase is very less, but I increases very high. The ratio is nothing but very less. So therefore mu is very less. And also, as the mu is very less, as I already told you, both are inversely proportional, so reluctance will increase. So therefore, whenever the mu is decreases, the reluctance will increase in the saturation region, because the slope is very less. So therefore we can say that here in a BH curve, during the linear region, the slope is a constant, so mu is constant. But in saturation region, the slope is not constant, because a very large increase in I will give you a very small increase in B. So therefore we can say the ratio is very less. So the ratio itself indicates the slope of the curve, which is equal to mu. As mu is very less, the reluctance of the core is very high in this unsaturation, or you can say in the saturation region, the value of the R is very high, whereas in the unsaturation region, the mu is equal to constant, so the reluctance of the core is also constant. So finally I can say only one thing, which is in the unsaturation region, the reluctance of the core is very constant, because the mu is a constant, whereas in the saturation region, as you increase the I, the magnetic permeability decreases, so its reluctance will be increasing huge and huge value. In electric circuit, R is independent of current flowing through it, but in magnetic circuit, R is dependent upon B. See, B is nothing but flux, so therefore we can say in electric circuit, R is independent of the current. See, the value of the resistance of any material is a constant, which is independent of the current flowing through it. But in magnetic circuit, the reluctance of the core is going to depend upon the B. It's a very important point. See, always in a transformer, we can see in an electrical circuit, the resistance is independent of the current flowing through it, but in a magnetic circuit, the reluctance of the core is going to depend upon the magnetic flux density. This is a very important point. We can say clearly that in electric circuit, the resistance of a circuit is independent of the current flowing, but in a magnetic circuit, the reluctance is going to depend upon the magnetic flux density. Transformer core is made by silicon steel because it is going to have the very high magnetic permeability. See, silicon steel is basically ferromagnetic material. So we are going to add basically the steel is a ferromagnetic material. So we are going to add this silicon to the steel because to reduce the brittleness. So therefore we can say that if you add more, it will become more brittle. So therefore we are going to decrease the resistivity, or we can say that we need to increase the resistivity of the steel. By adding the silicon, we are going to increase the resistivity of the steel, because to reduce the current losses we need huge amount of resistivity, but not the permeability. So therefore this silicon is not at all changing the permeability of this core, but it is changing the resistivity, or we can say that it is going to increase the resistivity of the core. So therefore we can say that we are going to reduce the eddy current loss. If you add more and more silicon, then we can say that it is going to become more brittle. The core is going to become more brittle in nature. So transformer core is basically made by silicon steel because it has the very high magnetic permeability. So silicon steel has the huge amount of magnetic permeability, so the reluctance of the core is very less. So we use this material to make the transformer core. Same flux density in the core, the current needed with air gap is more than the current needed without air gap. So therefore, for same flux density in the core, the current needed for the air gap is more than the current needed without air gap. Suppose if you want to make a constant magnetic flux both in the core and also the air gap in the core, then definitely we can say we need a huge amount of current. We need huge amount of current, because with the help of air gap, the permeability of the air gap is less, but reluctance is very high because both are inversely proportional. As reluctance increases, if you want a constant flux, then you need huge amount of current, because N into I is equal to phi into R. So as R increases and you need a phi value constant, then definitely you have to increase the I. Then only we can make this phi is equal to constant, because phi is equal to Ni by R. Is as R increases, then you have to increase the I. Then only the ratio will be equal to constant. So therefore we can say that for same flux density, the same flux density means flux. So whenever the flux is constant, the flux density is also constant, because flux density is equal to flux per area. So for same flux density in the core, the current needed with air gap is more than the current needed without air gap. So if you go for the air gap, the reluctance of the core increases. So therefore the Ni is equal to phi into R. So phi is equal to Ni by R. As R increases, definitely you have to increase the current to make the flux is equal to constant. So whenever the flux is equal to constant, the magnetic flux density is also constant. For a constant MMF, the core with air gap has the lesser inductance than without air gap. So for a constant MMF, the core with air gap have lesser inductance than without air gap. See, I've already told you L is equal to N square by R. So R is equal to L by mu A. So finally you are going to get L is equal to N square into mu A by L. See, for a air gap, if you have a air gap, the magnetic permeability is less for a air gap. So therefore, there the inductance is less. But if you use a core, then definitely mu is equal to higher. So therefore, the inductance is also higher. So therefore, for a constant MMF, the core with air gap have lesser inductance than without air gap, because inductance is proportional to magnetic permeability. For air gap, the permeability is less, so therefore the inductance of the coil is very less. But if you move the coil on the iron core, its permeability is very high, so inductance is also very high. So therefore, if you want to increase the inductance of a coil, then keep a iron core between them. So therefore, suppose if you are going to turn some coil, if you keep it in a air gap, the inductance is very less. But if you keep a core between them, between the coil, if you keep a core, then its inductance increases because inductance is directly proportional to magnetic permeability. So more is the magnetic permeability of the core, more will be the inductance. Then hysteresis loss is equal to Kh into F into V max to the power of x, where x is equal to 1.6, whereas eddy current loss is equal to K into F square into V max square. See, I have already told these basic equations. See, you can see Kh is called as the, this hysteresis coefficient constant. This depends upon the volume of the core, and K is called as the eddy current, or we can say that simply we can say eddy current coefficient. This depends upon the type of material in core and thickness of the core. It is going to depend upon the material of the core and also thickness of the core. So you can say clearly hysteresis loss means whenever there is a magnetization and demagnetization effect. So because of those, the dipoles are going to get overchange its direction, they are going to orient their direction. So because of that, a small amount of energy is consumed by the dipoles. It is called as the hysteresis losses. Whereas eddy current loss means because of the resistivity of the core, the circulating currents are going to get formed. So because of that, a small amount of loss is also going to happen in the core. It is called as the eddy current loss. And the summation of the hysteresis loss and the eddy current loss is called as the iron loss or the core loss in a transformer. Where Kh is called as the hysteresis coefficient, it is going to depend upon the volume of the core. So more is the volume of the core, more will be the hysteresis losses. And K is called as the eddy current coefficient. This is going to depend upon the type of the material you are going to choose in the core and also thickness of the core. The leakage flux in normal transformer is very high when compared to core type transformer. It is very high when compared to shell type transformer. So we can say the leakage flux. The leakage flux means the flux which is linking with its own coil. If it is not linking with any two other coils, with any other coil, it is called as the, if it linking with both the coils, it is called as the mutual flux or useful flux. If the flux is linking with its own coil, then we can say it is said to be leakage flux. So leakage flux means the flux which is linking with its own coil is called as the leakage flux, whereas the mutual flux means the flux which is linking both the coils is called as the useful flux or mutual flux. Only with the help of mutual flux only the power is going to get transferred, but not with the leakage flux. Only with the mutual flux only the power is transferring from one winding to another winding by electromagnetic, or we can say by using the magnetic medium. So in the normal transformer, the amount of leakage flux is very high when compared to core type transformer, when compared to shell type transformer. In a shell type transformer, we are going to use a sandwich winding. On one winding we are going to use other winding, so therefore the leakage is very less because the flux is going to link both the coils always. So therefore we can say the leakage flux is less, so more amount of power transfer is going to happen in the case of shell type transformer rather than the demand transformer. So more is the leakage flux, less is the power transfer. So more is the leakage flux, less is the power transfer between the coils. So we can say simply the leakage flux in the normal transformer is very high when compared to core type transformer. It is very high when compared to shell type transformer. The core type transformer is used for high voltage applications. So the core type transformer is basically used for high voltage applications because window is present. So you can see clearly a window is going to present in a core type transformer. So because of that only we are going to use for high voltage applications, and low voltage winding is kept on the two limbs, and over that high voltage winding are placed. See, always in a core type transformer, very important point that you always need to understand, always we keep the LV winding on the core first, and over that we are going to keep the HV winding, because more is the HV winding, we need more amount of insulation and more amount of cooling. So for LV we need less cooling, but for HV we need more cooling. If you keep the HV winding inside near the core, and over that if you keep LV, the cooling, we can't provide cooling for the HV winding, but if it is placed outside the LV winding, then we can easily provide the cooling effect. That is the reason on the core we are going to wound the first LV winding, and then we are going to wound the HV winding over that LV winding. So therefore this is a very important point. Because of that reason only, to provide the cooling for HV winding, we are going to provide it over the LV winding. So more is the voltage of the winding, more is the insulation is required. So therefore the core type transformer is basically used for high voltage applications because a window is going to get present, and also the low voltage winding is kept on the two limbs, and over that high voltage windings are placed. This is a very important concept regarding the core-type transformer. In a core-type transformer, there is a window is present. So because of that only, it is used for the high voltage applications. And on the two limbs, we are going to keep first the LV winding, and then over that we are going to keep the HV winding. Transformer is used for low voltage applications because window is present. So shell type is absent basically. So shell type transformer is used for low voltage applications because window is absent. So we can say the shell type in a shell type transformer, window is not at all present because the gap is totally occupied by the winding itself. So therefore we can say that it is used for the low voltage applications because the window is absent there. Whereas the core type transformer is used for the high voltage applications because the window is present. Whereas shell type transformer, a window is not present. So therefore we can say it is used for only low voltage applications. So I kept my mesh a dot in one of the winding and insert current into it. And now in another winding, keep dot and pass current into it. If this new flux supports the original flux, then dot is correct. See basically how to mark the dot and the windings. It's a very important concept. Listen carefully. See the concept of making the dot, marking the dots on a coil is, suppose if you take one coil and if you mark the dot there, and if you can mark dot at any one of the terminal and you try to pass the current inside that dot, and with the help of right hand thumb rule try to figure out the curl your fingers in the direction of the current, and the thumb is going to show you the flux direction. Then if you take another new coil and randomly keep a dot, randomly keep a dot at any one side of the terminal, and now also you are going to inject the current into the dot terminal of this new coil, and with the help of right hand thumb rule curl your fingers in the direction of the current, and thumb is going to show the direction of the flux. If this flux is supporting the original flux direction, then we can say whatever the dot that you have marked is always correct. It's a very important concept. So I kept my mesh dot in one of the winding and insert current into it, and now in another winding keep dot and pass current into it. If this new flux supports the original flux, then the dot is always correct. So this is the procedure by which always you have to mark the dots in the coils. I am repeating it again, listen carefully. Suppose I am going to take one coil and I am going to mark a dot at any one end of the terminal, and I will pass that current into the dot, and with the help of right hand thumb rule I will curl my fingers in the direction of the current, and thumb is going to show the direction of the flux. Now if I take the new coil, another new coil, and I will randomly keep a dot, and if I pass the current into the dot with the help of right hand thumb rule, I will curl my fingers and I will find the direction of the flux. If this flux is supporting the original flux, if it is in the same direction of the original flux, if it is supporting the original flux, it is said to be correct way of marking the dots on the coils. The secondary induced voltage of transformer is independent of load variation for a fixed supply. See, always the secondary induced voltage is independent of the load. Whether load is present or whether load is absent, it is independent of the load. It is going to depend only on the turns ratio and the primary induced voltage, because E2 by E1 is equal to N2 by N1. We can say clearly E2 is equal to N2 by N1 into E1. So this depending only on the turns ratios and also the primary induced voltage, but it is independent of the variation of the load. So therefore we can say that the secondary induced voltage of transformer is independent of load variation for a fixed amount of supply. So transformer won't allow DC input voltage to its secondary terminals. As I already told you, even if you give AC and DC combination to the primary coil, but always in the secondary you will always get a AC, but you will never get a DC, because for a DC supply there will be no change in flux, then there will be no induced current, so there will be no induced voltage. This is a very important point because of the Faraday's law. I have already told you, whenever there is a rate of change of flux, then only we are going to get a induced EMF. So whenever there is a rate of change of flux, then only we are going to get a induced EMF. With constant DC supply, the current is a constant, the flux is constant, so there will be no rate of change of flux, so there will be no rate of change of induced EMF. So we can say that for a transformer, if you give input as AC and DC combination, but output will be always purely AC, there will be no DC component, because this principle is going to be based on the electromagnetic induction. Whenever there is a rate of change of flux only, we are going to get a EMF induced. So for nonlinear BH curve, in order to produce the sinusoidal flux in the core, the exciting current is peak in nature and is rich in third harmonic component. In a non-linear BH curve in order to produce the sinusoidal flux in the core. The exciting current is peaky in nature and it is rich in third harmonic component. These things I've already told you. Suppose BH curve is we can say non-linear in fashion, then what is going to happen? The y-axis B and x-axis H. So therefore, H is directly proportional to I and B is directly proportional to flux. Suppose if I want to make the flux as pure sinusoidal, then definitely I need to give a peaky amount of current to the winding, then only I am going to get a pure sinusoidal, because I have already told you in a saturation for a huge amount of increase in current, a small amount of increase in flux will be happening. So you need to give a peaky amount of current in saturation region to get a flux of sinusoidal. So therefore simply we can say that if a BH curve is non-linear, then definitely you have to provide, if BH curve is non-linear, definitely you have to provide a peaky current waveform, then only you are going to get a sinusoidal flux. Peaky means I have already told you maximum, or we can say third harmonic component as dominant. I have already told you for flat form, for a flat top waveform and the peaky waveform, the maximum, or we can say the dominant harmonic is the third harmonic component. So therefore, for non-linear BH curve, in order to produce the sinusoidal flux in the core, the exciting current is peaky in nature and it is very rich in third harmonic component. So let me take a simple diagram here. This is the voltage source of V of t and this is the current of I of t which is passing through this voltage source. Let me assume V of t is equal to V1 plus V2 into sine of omega t plus theta 2 plus V3 sine of 2 omega t plus theta 3. Like this we are going to get here. This is also 2 actually, but I have written very wrong. This is 1, 2, 3, okay, it is also 3. Now I of t is equal to I1 plus I2 sine omega t plus phi 2 plus I3 sine 2 omega t plus phi 3. Then what is the average power sent by this source is? The average power is nothing but just we have to go for the, see these are the DC values, just you have to do the multiplication of the DC values, which is V1 I1 plus these are the AC values. Then we have to take the corresponding frequency components. If this is omega t, here also we have to take the omega t but not the other one. So therefore, if this is omega t, definitely there should be another omega, otherwise it will be 0. So here this call as the, this take the RMS value of this voltage, which is V2 by root 2 into the RMS value of this component is I2 by root 2 into the cos of phase difference between these two signals, which is theta 2 minus phi 2, you can take any value. So therefore we are going to get, so V2 by root 2 into I2 by root 2 is nothing but V2 into I2 by 2 into cos of phase difference between these two signals, theta 2 minus phi 2. So you can see if we take off inside, we are going to get V2 I2 by 2 into cos of theta 2 minus phi 2 plus, again same principle, here there is a 2 omega t, here also there is a 2 omega t. So therefore RMS value of this is V3 by root 2 into RMS value of this is I3 by root 2 into cos of phase difference between these two signals, which is theta 3 minus phi 3. So therefore if you take half inside, we are going to get V3 I3 by 2 into cos of theta 3 minus phi 3. So this is the principle that you always have to keep notice here. So if the DC values just to do their product, and if you take the AC values, just the same frequency component that you have to take, the RMS value of the voltage, the RMS value of the current into cos of phase angle between those two signals. Like that you have to do this one to get the average power which is sent by this source. So this is basically a transformer. So two winding transformer, it's a primary winding and secondary winding. So I've already told you, let me take a coil in this fashion. I'm going to move the primary coil in this fashion on the core, and let me assume this is the dot terminal, and I've already told you, you have to send the current inside this dot. So by using the right hand thumb rule, if I curve my fingers in the direction of the current, the thumb is going to show the direction of the flux, it is upward. And if you pass the flux here, the flux in this core is downward. So I have already told you, you have to mark a dot and you have to send a current inside that. The flux here, it should support the original flux. If I assume the dot is here and if I send the current inside, by the right hand thumb rule, the current is entering here. So if you curl your fingers in the direction of the current, the thumb is in the downward direction, the flux. So this flux is going to support the original flux. So therefore we can say this dot is very correct. So therefore in a transformer, if this dot is positive, simultaneously this dot is also positive because they have the same polarity. The dot means they have the same polarity. If this is positive, then this is also positive, which is plus or minus E1 means plus or minus E2. If this dot is positive, means this dot is also positive. In a transformer, if current is entering in one of the dot, then in the other winding the current will be always leaving. It's a very important point. Listen carefully. In a transformer, If a current is entering the dot, means in the under coil, the current will leave the dot. It's a very important principle in a transformer. In a transformer, if a current is entering in one of the dot, means in the other winding, the current will leave the dot. So now E1 by E2 is equal to N1 by N2, and I1 by I2 is equal to N2 by N1. This is a very important point that you always need to. These are the sign notations. These are basically sign sensitive equations. So this is always plus or minus E1, this is plus or minus E2, this is I1 and this is I2. The directions are always fixed. So these are the post directions of the current. So therefore, these are sign sensitive equations, which is E1 by E2 is equal to N1 by N2, I1 by I2 is equal to N2 by N1. These are basically sign sensitive equations, or we can say these are sign sensitive parameters. Always, this is a convention that you always need to follow. Suppose if I take I2 is inside, then it is a negative value. There is a reason. These are called as the sign sensitive equations. So the above both two formulas are purely sign sensitive. So this is the convention that you always have to follow. These are sign sensitive equations. If you take reverse, then you have to take the negative value there. So therefore, this is the sign convention that we are going to always follow. Which is E1 by E2 is equal to N1 by N2, and I1 by I2 is equal to N2 by N1. In a DC circuits, the power is conserved. In AC circuits, the complex power is conserved. That is in both active power and reactive power. I have already told you in a DC circuits, basically the power is conserved, means whatever the input power is equal to output power. So therefore, it is called by Thevenin's theorem. Whereas in the AC circuits, the complex power is conserved, means both the active power and also the reactive power is conserved. So because S is equal to P plus JQ, so if S is conserved, means P is conserved and also Q is conserved. So therefore, in DC circuits, always the power is conserved, whereas in AC circuits, the complex power is conserved. Therefore, we can say that both the active power and also the reactive power are conserved. The percentage voltage drop of the transformer at any given load is other than full load is. So therefore, we can say that the amount of percentage voltage drop of the transformer at any given load is other than full load. Suppose let me take a load as a rating of P2 and Q2. The load is having a rating of P2 and Q2, and I want to find what is the percentage of voltage drop of the transformer at any given load. The percentage of voltage drop means the drop in the internal winding, how much amount of voltage drop. The percentage of voltage drop is equal to percentage of voltage drop in the resistor into P2 by S plus the percentage of voltage drop in the reactance part into Q2 by S. So this is the basic formula. Suppose if you want to find what is the voltage drop, the amount of voltage drop in the internal impedance of the transformer is equal to the voltage drop in the resistive part into P2 by S plus the voltage drop near the reactive part into Q2 by S, where P2 is called as the rating of the load, the active power demand of the load, and Q2 is the reactive power demand of the load, and S is the overall rating of the transformer. So this is a very important formula. So therefore, the percentage of voltage drop in the internal impedance of the transformer is equal to percentage of voltage drop in the resistive part into P2 by S plus the percentage of voltage drop in the reactive part into Q2 by S, where S is the rating of the transformer and P2 is the rating of the load, active power rating of the load, and Q2 is the reactive power demand of the load, where S is called the rating of the transformer and P2 is called as the active power of the given load, and Q2 is called the reactive power of the given load. I have already told these important points. So percentage of voltage drop is equal to percentage of VR into P2 by S plus percentage of Vx into Q2 by S, where S is called the rating of the transformer and P2 is called as the active power of the given load, and Q2 is called the reactive power of the given load. See, auto transformer is suitable only when K is less than or equal to 1 or very close to 1. So we are going to use auto transformer only for this range, whenever the K is always less than or equal to 1 or very close to 1, where K is called the transformation factor. So the auto transformer is suitable only for whenever the K value is always less than or equal to 1, or simply we can say that very close to 1. Saving of copper is better when K is very close to 1. I have already told you, with the help of auto transformer, if you want the same rating, then we are going to use less amount of copper. So therefore we are going to save the copper. If the copper weight is same, means always, if you are going to use the same copper weight, means always the rating of the auto transformer is always higher than the rating of the two-winding transformer. But if you want to make the same rating, then you have to then you have to remove some amount of the copper. So therefore we are going to see the amount of copper. It's a very important point. If you are choosing the same amount of copper weight, then definitely the rating of the auto transformer is always higher when compared to the rating of two-winding transformer. But if you want to make the same rating, then you have to remove some of the copper winding in auto transformer. So therefore definitely now you are going to save the amount of copper in auto transformer when compared to two-winding transformer. So saving of copper is better when K is very close to 1. So inductive power transfer is equal to, I have already told you this important formula, which is inductive power transform. So inductive power transfer is equal to, which is 1 minus K into PIN. This point I have already told you, the inductive power transform is equal to 1 minus K into PIN, or you can say input power. So therefore the amount of inductive power transfer is equal to 1 minus K into PIN. K is always less than or equal to 1. K is called the ratio of the low voltage of the auto transformer by high voltage of the auto transformer. So K is nothing but it's the ratio of the low voltage of the auto transformer by high voltage of the auto transformer. So 1 minus K into PIN. So therefore K is nothing but it's the ratio of the low voltage of auto transformer by high voltage of the auto transformer. And this is the input power. So therefore, suppose if you want to know what is the conductive power transformer, which is input power minus inductive power transformer, we are going to get K into PN, where K is called the transformation factor. It is always less than or equal to 1. So therefore, simply we can say it is the ratio of the low voltage of the auto transformer by high voltage of the auto transformer. So this is the very point that you always need to understand. So therefore, the inductive power transformer is equal to 1 minus K into input power, and the conductive power transformer is equal to K into PN, because inductive power transformer plus conductive power transformer is nothing but is equal to overall input power. Where K is nothing but is always less than or equal to 1, it is equal to low voltage winding of auto transformer by high voltage of the auto transformer. In auto transformer, under ideal case, always the input power is equal to output power. Suppose if there is no losses in auto transformer windings, then we can say that whatever the input power is equal to output power. So in auto transformer, under the ideal cases, there is no losses in the winding of auto transformer, so therefore the input power is equal to output power. Two-winding transformer, in which power is transferred only by induction, but in auto transformer power is transferred by both induction and conduction. These things I have already told you. In a two-winding transformer, the power is transferring from primary winding to secondary winding by only induction process. But in auto transformer, the power is transferring from both induction and also the conduction process. So the inductive power transformer is equal to 1 minus K into power input, and the conductive power transformer is equal to K into power input. These things I have already told you. And in a DC motor or DC generator, the amount of EMF generated is equal to P5 into M by 60 into Z by A. I have already shown you the derivation of this formula also. So if you do the manipulation of this one, we are going to get simply P into Z by 60A into N5. So Eg is equal to Ka into N5. So Eg is equal to this K is a constant. K is nothing but is a constant, which is Pz by 60 into A. So Eg is equal to Ka into N5. So therefore, the EMF generated is directly proportional to the speed of the shaft and also the flux which is flux per pole which is generated. So E is directly proportional to N into phi. N is called as the speed of rotation of the shaft, and phi is called as the flux per pole. Armature reaction is eliminated by using the series winding and the interpoles. Series winding is connected in series with the armature winding. I have already told this point. Basically, the series winding means it is called as the compensating winding. So we are going to eliminate this armature reaction with the help of both interpoles and also the compensating winding. Series winding is also called as the compensating winding. Compensating winding we are going to place it on the pole shoes. This concept I have already told you. So therefore, armature reaction is eliminated by using the series winding or compensating winding and the interpoles. So therefore, series winding is connected in series with the armature winding. So always I have already told you, the armature winding, the interpole winding and the compensating winding, all these three windings are going to connect in series fashion. This concept also I have already told you. So therefore, always the armature winding, interpole winding and the compensating winding or series winding, all these are connected in series. So therefore, we can say that armature reaction means whenever the armature flux and the main field flux are going to interact with each other, there is a distortion in the overall flux. It is called as the armature reaction. So we can reduce this by keeping the interpole winding and also the compensating winding in series with the armature winding. All these three are connected in series fashion. DC shunt motor is used for constant speed applications like lathe machines, drilling, spinning machines, paper industry, woodwork, etc. I have already told you DC shunt motor is a nearly constant speed motor. From no load to full load, the amount of variation of speed is very less when compared to other motors. So that is the reason it is called as the constant speed motor. So DC shunt motor is basically called as the constant speed motor because the amount of change of speed from no load to full load is very less. So because of that only we can call it as the constant speed motor, and it is basically used in the lathe applications, drilling, spinning machines, and also the paper industry and the woodwork. So these are the places we are going to mostly prefer the DC shunt motor. The DC series motor N is directly proportional to EB by phi. At light load or small loads, phi is very small, so speed is very huge. So never operate the series motor under the no load condition because as IA increases, flux increases, so speed decreases. See, I already told you in a DC series motor, you never have to operate at the no load condition. If you operate at no load condition, the amount of current drawn is very less, so flux is very less, so speed will be very high because at no load the voltage drop in the array is very less, so therefore EB is nearly equal to supply voltage. So V is very high but flux is very less, so therefore the ratio is very high, so therefore the speed will be very high. So therefore we can say that that is the reason you never have to operate the series motor at the no load condition. So therefore simply we can say that in a DC series motor at no load condition, the amount of current drawn IA is very less. So IA into RA is also very less. So therefore EB is nearly equal to supply voltage. Whereas flux is very less because the armature current is very less. So EB by phi, its ratio is very higher. So therefore we are going to get a huge amount of speed. So therefore simply we can say that at no load the speed is very high, which is very dangerous speed. That is the reason you never have to operate the series motor under no load. Means always you have to keep it low and then only you have to on the supply. So therefore in a DC motor, N is directly proportional to EB by phi. At light load or small loads, the current drawn is very less. So therefore the flux is also very small. So speed is very huge because EB is nearly equal to supply voltage. So never operate the series motor at the no load condition. As the load increases, IA increases, so flux increases, then speed decreases. So therefore whenever you increase the load and a DC series motor, the amount of current drawn increases, so flux increases, so therefore the will decrease. It's a very important point. So we can say that in a DC series motor, whenever the load increases, the current IA increases, so flux increases, the speed decreases. Then we are going to get a graph which is called as a hyperbola graph with respect to speed and the current and IA. So therefore the variation of speed is very huge in case of DC series motor. See, whenever the current IA is equal to 0, the speed is very huge. But whenever the current is very huge, the speed is very less. So we are going to get a rectangular hyperbola for a DC series motor. This concept also I have already told you. DC series motor is used in variable speed applications like electric trains, cranes, elevators, air compressors, vacuum cleaners, grinders in kitchens. See, I already told you DC series motor. DC series motor, the speed curve, just now I told you it is a rectangular hyperbola. It means you can see a huge amount of variation of speed we can get in the terms of the DC series motor. Means whatever the speed you want, you can easily get with the help of DC series motor. So this is called as a variable speed application. So that is the reason it is having variable speed as the changing load is happening. So therefore we can say it is used in the variable speed applications like electric trains. In electric trains we use the DC series motor, and the cranes, elevators, and the air compressors, vacuum cleaners, and the grinders, and also in the kitchens, in the grinders and kitchens. In all these places we are going to use series motor because see, the beautiness of the series motor is it is applicable for both DC supply and also AC supply. That is the reason it is called as a universal motor or single phase motor. So DC series motor is also called as a universal motor because it can work perfectly for both the AC supply and also for DC supply because of its variable speed applications. So it is mostly used in the electric trains, cranes, elevators, air compressors, and the vacuum cleaners and grinders in kitchens because where we need the variable speed of the rotor of the shaft. Eventually compound DC motor, the net flux is equal to phi SH minus phi SC. We are going to always assume that phi SH is always greater than phi SC. As the load increases, then the current IA increases. So therefore phi SC increases. So therefore this overall flux is always decreases. We are going to assume the shunt flux is equal to constant. So therefore in a differentially compound DC motor, the resultant flux is equal to shunt flux minus phi SC. As the load increases, the current IA increases, so phi SC increases, so therefore the resultant flux will decrease because we are going to assume the shunt flux is a constant. So therefore, we can say that is the reason. See, as the load increases, the series flux increases, so resultant flux decreases, so its speed will increase. So its speed will increase. So we can say in differentially compound DC motor, the resultant flux is equal to shunt flux minus phi SC. We are always going to assume the shunt flux is greater than the series flux. So whenever the load increases, the current IA increases, so phi SC increases, so the resultant flux decreases. We are going to assume the shunt flux is constant. So what is going to happen? As the resultant flux decreases, I have already told you N is directly proportional to AB by phi. As phi decreases, then N will decrease. So we are going to get an increase in speed for the increase in load. So we are going to get a above characteristics. These characteristics I have already shown in the differential compound DC motor characteristics. Whereas in the cumulative compound DC motor, the resultant flux is equal to shunt flux plus the series flux. As the load increases, then IA increases. So as load increases, the current IA increases. So series flux increases. So therefore the overall flux increases. So therefore we are going to assume the shunt flux is constant. So as the resultant flux increases, the speed will decrease here. So therefore it is vice versa of the differentially compound DC motor. So in a cumulative compound DC motor, the resultant flux is equal to phi SH plus phi SC. So as the load increases, the current IA increases, phi SC increases, so the resultant flux increases. We are going to assume phi SH is constant. As I have already told you, N is directly proportional to AB by phi. As phi increases, N decreases, so N is going to decrease. The variation of the speed, the graph is going to lie between the DC shunt motor and also the DC series motor. This cumulative compound DC motor is going to lie, the graph is going to lie between the DC shunt motor and also the DC series motor. Whereas the differentially compound DC motor, its graph is going to lie above the, I am talking about the speed and the load, or we can say N and IA, or speed and torque. You can go for anything because speed and torque, or speed or NA, IA, because torque is directly proportional to IA. So therefore both the graphs are same. So therefore the speed will increase here and the speed will decrease here. The characteristics of DC compound motor are in between that of the DC series and the DC shunt motor. This concept I have already told you. The characteristics of the DC compound motor are in between that of the DC series and the DC shunt motors, whereas DC differential compound motor, it will have the graph above the DC shunt motor. This concept I have already told you by showing the graphs in the DC machines itself. Sometimes output is 0. When motor on no load or generator on no load. See, whenever motor is on no load, what is going to happen? As I have already told you, the current at the no load condition, the amount of current drawn is nearly equal to 0. So output power is equal to EB into IA. It is nearly equal to 0. So therefore the output power is equal to 0. Similarly, generator on no load. At no load condition, the current drawn by generator is 0. So output power is also equal to 0. So therefore, the output power is 0 at these conditions whenever the motor is at the no load condition or the generator is at the no load condition. So therefore, at no load conditions for both motor and generator, the output power is equal to 0. Power loss is equal to copper power loss. See, copper loss plus core loss plus friction windage loss is called as the total losses. So in the DC machines, we can say the copper loss plus core loss plus friction loss. These are the losses which are going to present in the DC machine. So therefore copper loss plus core loss plus friction windage loss is also called as the mechanical losses. So input is always equal to output plus losses. The losses in the DC machine are basically copper loss plus core loss plus friction windage losses. So total input power is equal to output power plus losses. DC machine can act like DC motor as well as DC generator. See, you have to build only one machine, which is a DC machine. That machine can work as a DC motor or whether it can work for DC generator. Only one machine can perform two functions. One is it can act like a DC motor or whether it can act like a DC generator based on the input that you are going to give. If you give electrical input, it is going to act like a DC motor. If you give mechanical input, it is going to act like a DC generator. But the machine is same, only one machine, but the way that you are using is different. So DC machine can act like DC motor as well as the DC generator. For demagnetization, use extra ampere turns in the main winding field, usually series field winding. So if you want to remove the demagnetization, I have already told you have to use the compensating winding. Compensating winding is series winding. So you have to use some extra turns in the field winding So therefore we can compensate that demagnetization. So therefore if you want to eliminate the demagnetization because of armature reaction, you have to use some extra windings on this field winding, then we can compensate it one. So for demagnetization, use extra ampere turns in the main magnetic field, usually series field winding. So if you want to remove the demagnetization effect because of armature reaction, then definitely you have to use more number of ampere turns, or simply we can say more number of turns of series field winding which you are going to use to get the flux. So if you use more, it is going to, these both field fluxes are opposite direction, so therefore we are going to remove that one. So therefore simply we can say use more number of turns, or simply we can say ampere turns. So for cross magnetization, use interpoles. For cross magnetization, use interpoles used to reduce the distortion of magnetic field and always shifts the position of brushes to MNA. See, for cross magnetization, what is going to happen with the help of cross magnetization? If you want to remove this cross magnetization, you have to use the interpoles. So basically, this cross magnetization is going to distort the magnetic field and is always going to shift the brushes from GNA to MNA. So therefore, I already told this important point. If you want to eliminate the demagnetization, use extra winding on the series field winding of the main field winding. You have to use the extra winding of the main field winding. If you want to eliminate the cross magnetization, then use the interpoles. Otherwise, what is going to happen if you are not going to use interpoles? Because of this cross magnetization, there is a distortion in the flux, and also we can say it is going to shift the brushes from GNA to MNA. So this is a very pain in the neck. That is why I recommend you to always use the interpoles to remove this cross magnetization effect. Because of demagnetization, the overall flux value will decrease, but with the help of cross magnetization, the overall flux value will never change, but only it is going to distort the waveform in the core, in the machine, in the air gap. So finally we can say that if you want to eliminate the demagnetization, use the extra series main field winding ampere turns to eliminate the demagnetization, and if you want to remove the cross magnetization, you have to use the interpoles. Then only we can remove it. Otherwise, what is going to happen? Because of cross magnetization, there is a distortion of the magnetic field. So therefore, it is going to shift the brushes from GNA to MNA. GNA is called as geometric neutral axis, and MNA is called as the magnetic neutral axis. Magnetic neutral axis means the axis which is perpendicular to the resultant flux. Critical resistance means RC is the slope of tangent of OCC curve linear part, which determines the maximum value of RSH so as to build voltage value. See, the critical resistance means it is a slope of the tangent of the OCC curve. It's a linear part which determines the maximum value of RSH so as to build up voltage. See, I've already told you regarding the OCC graph with respect to induced voltage, no load induced voltage and the field current. You are going to get a OCC curve there. Then I've already told you one important point. If you draw a straight line, this tangent to this graph, then we are going to get the slope is called as the critical resistance. So always, whatever the field resistance should be always lesser than the RC. Then only the graph between the field resistance and the OCC are going to get intersect. Then we are going to get a point of operation. If the shunt resistance is greater than critical resistance, the two graphs are not going to intersect with each other. So there will be no point of operation. So there will be no build-up of voltage. So always RSH should be always less than RC, or simply we can say RC is always greater than RSH. Then only the two lines are going to get intersect. One is called OCC and the other is called as the EF is equal to IF into RSH. If these two lines are intersecting, then only there is the point of operation. So therefore the voltage is going to get built up. Otherwise, there is no point of intersection, means there is no build-up of voltage. In a DC shunt generator, which is Eg minus Ia into Ra is equal to V, it is called as the terminal voltage. So generated voltage minus armature drop is equal to terminal voltage when armature reaction is neglected. Suppose if you take the armature reaction drop, Eg minus Ia Ra minus armature reaction drop is equal to terminal voltage when the armature reaction is included. So therefore, by using the armature reaction, the terminal voltage will further decrease. So because of armature reaction, the terminal voltage further decrease. But here there is a less decrease of terminal voltage, but here more decrease of terminal voltage because of this armature reaction drop. So in a digital generator, Eg minus Ia Ra is equal to V. It is when the armature reaction is neglected, which is Eg minus Ia Ra minus armature reaction drop is equal to terminal voltage whenever we are going to consider the armature reaction. So you can see clearly the drop of terminal voltage is very less if you are not going to consider the armature reaction, but if you consider the armature reaction, the amount of change of the terminal voltage is very higher. Cumulative compound DC motors are useful in intermittent loads, sudden loads like punching machines. It is used in coal conveyors. See, I have already told you, cumulative compound DC motors will have the graph which is lying between the DC shunt motor and the DC series motor. So it is useful for basically intermittent loads, means very sudden variation of loads like punching machines, and also it is used in the coal conveyors. So in these two applications, we are going to use the cumulative compound, and I have already told you the graph of the cumulative compound characteristics are going to lie between the DC shunt motor and the DC series motor. So it is basically used for the sudden variation of the loads. Sudden variation of the loads is basically happens in the coal conveyors and also in the punching machines. It's a very important formula. The temperature at resistance 2 is equal to the temperature at resistance 1 into 1 plus alpha into T2 minus T1. So the temperature at resistance T2 is equal to the resistance at temperature T2 is equal to the resistance at temperature T1 into 1 plus alpha into T2 minus T1. So R2 is equal to R1 into 1 plus alpha into T2 minus T1. This is called as the temperature at resistance T2, and this is the resistance at temperature T1, which is into 1 plus alpha into T2 minus T1. It's a very basic equation. And always the armature current is equal to supply voltage minus back EMF by Ra for a DC motor. For a DC motor, Ia is equal to V minus Ed by Ra. So during starting, I have already told you, during starting, I have already told you the speed is 0 because it is not at all rotating. So Eb is equal to 0. So therefore, V by Ra, and Ra is very less. The current draw is very huge. So Ia is very huge value. So to limit this huge current, starters are used. So basically, the starters are going to limit the starting current only. It is just a protective device at starting. It is basically a protective device. It is used at starting. So at starting, we are going to get a huge current in the armature. So to protect the windings from this huge amount of current, we are going to use the starters. So we can simply say it is said to be a protective device at starting purpose only. It is a protective device which is used for the starting purpose only. So therefore, simply we can say that the starters are going to use to eliminate the Ia with a very huge value. So therefore, it can limit it to a certain limit value. So starters are nothing but which are basically protective devices which are used at the starting purpose only. So now we discuss about the armature voltage control. Armature voltage control means suppose if the voltage supply voltage increases, then the armature current increases. So therefore the torque increases. So therefore the speed increases. Whereas if the supply voltage decreases, the current Ia decreases, so torque decreases, so speed decreases. It is said to be armature voltage control. Suppose if I am going to increase supply voltage, the amount of current drawn will increase. So torque will increase because torque is directly proportional to Ia. So torque increases. As torque increases, the speed will increase. It's a very small way of visualizing it. As torque we are going to increase, the speed will increase. Similarly, as the voltage decreases, the current Ia decreases. So therefore, the torque decreases, so speed will decrease. This is called as the armature voltage control. And I already told you the DC machines, N is directly proportional to Eb by 5. Suppose, let me assume the Eb is a constant value. Then, as flux decreases, the speed increases. As the flux increases, the speed will decrease. It is called as the field control. But always we choose the field weakening, but not a field increase, because with always in saturation, we never use this case. We only use the field weakening control. So therefore, field control is only used for the field weakening. So it is used only for high speed applications. It's a very important point that you always need to understand. I have already told you electrical angle is equal to mechanical angle into P by 2. So electrical angle is equal to P by 2 into mechanical angle. P is called number of poles. The number of poles are always even number. So electrical angle is equal to P by 2 into mechanical angle. So the number of poles are always even number. So electrical angle is equal to P by 2 into mechanical angle. We need transformer to transfer huge power over large distance with less losses. I have already told you, with the help of transformer, we are going to use the stepping up. Suppose if you go for stepping up process, the voltage increases and current decreases because power is always constant. So P is equal to V into I. So with the help of step up transformers, if you increase the voltage, the amount of current in the winding will decrease. So that current should pass through huge amount of distance. So therefore the losses are very less. So therefore we can say that it is with the help of transformers we are going to transfer the huge power through a long distance with less losses. This is the basic need of the transformer. So we need transformer to transfer huge power over large distance with the help of less losses. That is why we use a transformer near the power station, so therefore we can boost the voltage to get less amount of current. As this current should pass through huge amount of distance, the resistance is very higher, so I square R will be lesser, so therefore less losses. So huge power can be transferred to the load centers with less amount of losses with the help of this using the transformers. See, CMOS test is basically it is did at the no load test. It is based, I already told you, CMOS test is basically a no load test. So this method is suitable for DC shunt motor but not for DC series motor, because DC series motor should never be operated at no load condition. So therefore this CMOS test is not operated for DC series motor, but it is only operated for the DC shunt motor and DC counter motors, but not for DC series motor. So we use the field test to find the efficiency. We basically use the field test to find the efficiency of this series motor, but with the help of CMOS test we are going to find the constant losses. If you know the constant losses, we can find the efficiency at any load condition. So therefore CMOS test is basically used to find the constant losses. It is basically no load test. It is only done for the DC shunt motor and also DC compound motor, but not for the DC series motor, because you never have to operate the DC series motor at the no load condition. So I have already told you the generated EMF and the back EMF in a DC motor, the formula is same, which is AB is equal to P phi into N by 60 into Z by A. Let me multiply 2 pi and divide by 2 pi here and here, then I am going to get like this, pi into 2 pi N by 60 into ZP by 2 pi A. This is called as the omega. This is called as the omega, and this is the flux, and this is called as some constant K, or K you can call any constant. So therefore AB is equal to K into phi into omega. Similarly, power is equal to torque into omega. So power is equal to torque into omega is equal to EB into IA, because EB into IA is called as the electrical power which is developed, which is converted into mechanical power, which is T into omega. So EBIA is called as the mechanical power developed to rotate the shaft. The power consumed in the shaft is nothing but P is equal to T into omega. So both should be always equal. So therefore T into omega. EB is just now we have seen, which is called as phi omega into Ka into Ia. So omega cancels, we are going to get T is equal to K into phi into Ia. So this is a very important formula. K is nothing but it is the same value for both these formulas. K is equal to Zp by 2 pi. It is a constant for a fixed machine. So therefore EB is equal to phi into omega into Ka. P is equal to T into omega is equal to EB into Ia. So T into omega is equal to EB is nothing but phi omega K into Ia. So omega cancels. We are going to get T is equal to K into phi into Ia. So therefore these are the two important relations that you always have to remember. So T is equal to K into phi Ia. EB is equal to phi omega into Ka. K value is same for both these equations, which is equal to Zp by 2 pi A. It's a fixed for a given machine. Hopkinson's test is also called as the regenerative test. Only the losses are consumed from the supply and the machines are fully loaded. I have already told you Hopkinson's test is basically a back-to-back test. We need to connect two identical machines. One is going to act like a motor and the other is going to act like a generator. So this Hopkinson's test is also called as the regenerative test. So whatever the input that you are going to give, it is totally consumed in the terms of the losses of both the machines. So therefore, with the help of this, we are going to find the efficiency of the given machines. So Hopkinson's test is also called as a regenerative test. Only the losses are consumed from the supply and the machines are fully loaded. So we are going to fully load them, and whatever the input that we are going to give, it is totally consumed in the terms of the losses. So we are going to use two identical machines which are connected back to back. So it is also called as a regenerative test. It is done on two identical DC machines. One acts as a motor and the other acts as a generator. I have already told this important point. Hopkinson's test is basically connected on two identical machines. One is going to act like it is basically done on two identical DC machines. One is going to act like a DC motor and the other is going to act like a DC generator. The flux lines will never intersect with each other. See, two flux lines will never intersect with each other. So this is a very important common point. For a given magnetic pole, the two fluxes will never they will never link with each other. So from outside, the flux goes from north pole to south pole. But from inside, the flux goes from south pole to north pole. So therefore, there is a closed path. Always there is a closed path for the magnetic flux. So now we will discuss one important formula which is called as the Ampere's law. So Ampere's law says that the closed line integral of b bar dot dl bar is equal to mu naught into I. So closed line integral of b bar dot dl bar is equal to mu naught into I. So therefore b by mu is nothing but h. So therefore the closed line integral of h bar dot dl bar is equal to I, because v is called the magnetic flux density, which unit is Weber per meter square. It is also called as Tesla, and the unit of h is called as the ampere per meter. H is called as the magnetic field intensity, and v is magnetic flux density, and h is magnetic field intensity, and the unit of flux is Weber. So magnetic flux density is equal to flux per area, so it is called as the Weber per meter square. As Ampere's law, the closed line integral of b bar dot dl bar is equal to mu naught into I. So therefore, if you take b by mu naught, b by mu naught is nothing but h, because v is equal to mu into h, so h is equal to v by mu naught. So therefore, the closed line integral of h bar dot dl bar is equal to current I. For same MMF, with introduction of air gap, inductance decreases. I have already told you here, inductance is directly proportional to magnetic permeability. As the magnetic permeability decreases, inductance will decreases. So air has less amount of mu value, so therefore inductance will decrease. Or simply in the other fashion also we can say L is directly proportional to N square by R. As the R increases, the L value decreases. With the help of air gap, there is a huge amount of reluctance, so therefore the L value decreases. You can go for any procedure, you will get the same result. L is directly proportional to mu, or L is inversely proportional to R. So in both the cases, we are going to get the same result. Rotor in induction machine is of two types, either wound rotor and the other is a squirrel cage rotor. So in the induction machine, there are two types of rotors. One is called as the squirrel cage rotor, and the other is called as the wound rotor, or simply we can say slip ring induction motor or slip ring rotor. Means we are going to use the winding on the rotor for increasing the starting torque. Whereas in the squirrel cage rotor, we are going to use bars, connecting bars, which are screwed together with the, and at the end we are going to use the end rings to make it short circuit. Always the starting torque in the wound rotor is higher when compared to squirrel cage rotor. The rotor in induction motor always have NR less than NS. So always NR less than NS. NR will be reduced further if we keep any load, but always NR will be very close to NS at any circumstances. I have already told you in an induction motor, I have already told you NR is always less than NS. If you increase the load, NR will decrease, but always this NR will try to make nearly equal to NS. It means a small amount of difference of NR will be there between the NS and NR, but not a huge value. So therefore, we can simply say that induction motor always rotate at a rotor speed which is less than synchronous speed. No matter whatever the load you apply, the speed will decrease. If you increase the load, the speed will decrease, but the NR will be very close to NS. There will be no big difference between NR and NS. It will be very small difference. So therefore, the rotor in induction motor always have NR less than NS, and NR will reduce further if we keep any load, but always NR will be close to NS at any circumstances. Is always perpendicular to the resultant flux direction. The conductors at this position won't cut the flux, so brushes are placed at these positions. I have already told you MNA, the magnetic field axis, is always perpendicular to the resultant flux direction. So at this position, if you place the brushes, there will be no flux. Whichever the coil which is going under the commutation, that coil will never intersect the flux. So no induced voltage, so no sparks. That is the reason we will keep the brushes at these positions. So therefore, MNA is always perpendicular to resultant flux direction. The conductors at these positions won't cut the flux, so brushes are placed at these positions. I have already told you, MNA means it's a magnetic neutral axis. It is always perpendicular to the resultant flux direction. So and if you keep a coils at this position, these coils will never intersect the flux. If they never intersect the flux, means no induced EMF at this coils. So whichever the coil going under this commutation at this process will never get any spark. So that is the reason we keep the brushes at this position itself. Whenever the load decrease or increase, this MNA will also change its direction. So we can't always shift the brushes from one direction to another direction. Whenever there is a change in load, always the magnetic neutral axis will also change its direction. It will change its place. So therefore, you never always have to keep the changes in the position of the brushes. So therefore, we go for some methods. Always we fix the brushes at the constant position irrespective of the change in MNA, because this MNA is occurring because of the armature reaction only. So we will try to reduce this MNA. So always we keep the brushes at a constant position only. The ampere turns per pole is equal to Zi by 2p. The ampere turns per pole is equal to Zi by 2p. And the ampere turns per pole is equal to, is called as the total ampere turns per pole. It is called as the total ampere turns per pole. So this is called as the total ampere turns per pole, which is equal to Zi by 2p. The total ampere turns per pole is equal to Zi by 2p, where I is called as the Ia by A. Where I means the current in one parallel path, which is equal to Ia by A. Therefore, simply we can say the ampere turns per pole is equal to Zi by 2p, where I is equal to Ia by A, where I is called as the current in one parallel path and I is called as the armature current. So therefore, simply we can say that the ampere turns per pole is equal to Zi by 2p and I is equal to Ia by A. Cross magnetization can be removed by making slots in pole. The cross magnetization can be removed by making slots in pole or pole shoe, and winding is done in series with the armature conductors. This is also called as a compensating winding, and another method can also be used. It is interpole method. I have already told you, with the help of interpole we are going to eliminate the cross magnetization, whereas with the help of compensating winding we are going to eliminate the demagnetization. So this is a very important point. With the help of interpole winding, we can say that with the help of interpole winding we are going to eliminate the cross magnetization, and with the help of compensating winding we are going to eliminate the demagnetization effect. So with the help of compensating winding we are going to eliminate the demagnetization effect, and with the help of interpoles we are going to eliminate the cross magnetization. This concept I have already told you in the subject itself of DC machines. The cross magnetization can be removed by making slots in pole or pole shoe, and winding is done in series with the armature connectors. This is also called the compensating winding, and the other method can also be used. It is called the interpole method. See, all the armature winding, interpole winding and the compensating winding, all these three are connected in series with respect to each other. Same current is flowing with each and every winding. The analogy of transformer in mechanical domain is gears. See, in electrical domain it's a transformer, and in the mechanical domain there is a gears. The concept of gears and the concept of transformer is same. They are going to be either increase or decrease the voltage in the transformer, and increase or decrease of the amount of work done in the gears. The work done is same, but only thing is the rotation of the speed is going to get changed. It is basically so therefore the analogy of transformer in mechanical domain is gears. The household we get 230 volt 50 hertz single phase supply. So in the basically in the domestic loads, whatever in our houses we are going to get in India, the RMS we can say that the phase voltage has a RMS value of 230 volt and a 50 hertz and a single phase supply. It's a single phase supply of RMS value 230 volt and a 50 hertz supply we are going to get. It is the standard one in India. So in household we are going to get single phase supply of 230 volt RMS and 50 hertz. The transmission voltages levels are 700 kV, 400 kV, 20 kV, 110 kV, 66 kV, 33 kV and 11 kV. So these are the transmission voltages which are present in the India up to now, which are the 700 kV, 400 kV, 220 kV, 110 kV, 66 kV, 33 kV and 11 kV. So these are the transmission voltages which are present right now in India. Ammeters measure RMS value in AC circuit. In AC circuit, always in AC circuit, whatever the meters that you are going to keep, they are going to measure the RMS value. So whatever the meters that you are going to keep in the AC circuit, they are going to measure the RMS value itself. Circuit cuts the stationary magnetic flux, then we get dynamically induced EMF. If circuit cuts the stationary magnetic field, then it is called dynamically induced EMF. It means that the magnetic flux is stationary, but the conductors are rotating. Then the EMF induced is called as a dynamically induced EMF. If the magnetic field is cutting stationary electric circuit, then we get statically induced EMF. See, dynamically induced EMF means the magnetic field is stationary, but the conductors are rotating. It is called as the dynamically induced EMF. But if the coils are stationary, if the circuit is stationary and if the magnetic flux is moving, it is changing with respect to time, then we call it as a statically induced EMF. Statically induced EMF in case of the transformers, and whereas in the rotating machines we are going to get the dynamically induced EMF. So in the static machines we are going to get the statically induced EMF, whereas in the rotating machines we are going to get the dynamically induced EMF. So whenever the coil is fixed, it is stationary and the field is rotating or field is changing with respect to time, it is called as the whatever the EMF which is produced in the coil, it is called as a statically induced EMF. Whereas the reverse process, which is the field is stationary, but the coil is changing its direction. It is rotating, it is cutting that flux. Then whatever the EMF induced in that coil is said to be dynamically induced EMF. So for generator we always use the Fleming's right hand rule. So because there is a R here, in generator there is a R here, so you have to use the Fleming right hand rule. And for motor we use the Fleming left hand rule. This concept I have already told you. So for generator we are going to use the Fleming right hand rule, and for motor we use the Fleming left hand rule. See, in generator the parameters which we know are called as the torque and also the magnetic flux, but we don't know the direction of the current induced. That we can figure with the help of this Fleming right hand rule. So here the thumb is going to indicate the force, and the forefinger is going to indicate the magnetic field, and the middle finger is going to indicate the current. But if you have to be very careful here by applying here Fleming right hand rule, whatever the force that you are taking, the thumb direction, it is the mechanical torque, not the electrical torque. Always, whether it is a generator or motor, always the electrical torque is always opposite to the mechanical torque. That is a very important point. But whatever the force, the torque direction that you are taking, as I already told you, for generator we are going to use the Fleming right hand rule, and for motor we are going to use the Fleming left hand rule. These concepts I have already told you in the basic machines itself. So therefore we can say simply that for DC generator we have to use the Fleming right hand rule, and for DC motor we have to use the Fleming left hand rule. See, FBI, it is easy to remember for both. So for both things it is the same principle, which is called as the, for thumb it will be force, and for forefinger it is a magnetic field, and for the middle finger it is a current. Same for even for this also, which is for thumb we are going to show the force, and for forefinger we have to use the magnetic field, and for middle finger we have to use the current. So in the Fleming right hand rule, in the generator the unknown quantity is the only current. We know the force, we know the magnetic field. See, this force is nothing but whatever this force is called as the mechanical force. This is the direction of the mechanical force, and this is the direction of the magnetic field. So if you use the right hand thumb rule, then you are going to get the direction of the current, which is called as the, to find direction of current in generator. So we are going to use this Fleming right hand rule to know the value of the direction of the current. Whereas in the Fleming left hand rule, the thumb is the force, which is the electrical force, or you can say electrical torque, and this forefinger is called as the magnetic field, and its middle finger is called as the current. So in the motor we know the value of magnetic field, we know the direction of current, but we do not the direction of the electrical torque. So we can figure out with the help of this Fleming left hand rule. So to find direction of the force or torque in the electrical torque in motor, we are going to use this Fleming left hand rule. So this is a very important point. So this force is called as a mechanical torque or mechanical force, and this is called as the electrical force or electrical torque. So this is called as the F cap is called I cap cross B cap. So this is the general formula that you can remember. For B cap is the direction of the magnetic field, and I cap is the direction of the electric current, and F cap is the direction of the electrical torque or electrical force. This is a very important point that you can apply for both motor and also for generator. You can apply this general principle, but here F cap is always going to represent the electrical force itself, and in a generator the mechanical force and electrical force are always opposite of each other. The electrical torque and mechanical torque are always opposite of each other, whereas in the Fleming, we can say in the type of motor, in the motor always we can say that in the motor the electrical torque and the load torque will be always opposite of each other. So in a generator the mechanical torque and the electrical torque are opposite of each other, whereas in the motor we can say simply that the electrical torque and the load torque are quite opposite of each other. So whatever F cap is nothing but it is always electrical torque. So here it is always the electrical torque. So you can apply this general principle, this general formula for both motor and also for generator. So in a DC generator, AC generator, DC motor, AC motor exist in this world. So the type of things that are going to exist in this world are the DC generator, AC generator, DC motor and AC motor. These are the things that are going to exist in this world, which is called as the DC generator, AC generator, DC motor and AC motor. So these are the four things that are going to present in this world, which is called as the DC generator, DC motor, AC generator and AC motor. So in a generator, always the torque supply should be always given on the torque electrical, which is always opposite to the supply torque.
then only the voltage is going to get produced. See, always in the generator, you need to rotate the shaft in the magnetic field. So whenever you are going to rotate the shaft, that is called as the torque is called as the supply torque, or you can say mechanical torque. Always for a mechanical torque, the opposition is called as the electrical torque. Means mechanical torque and electrical torque will be always opposite direction. So therefore we can say that whenever the mechanical torque is greater than the electrical torque, then only we can say that the voltage is going to induced in the coils of generator. So in a generator, the electrical torque or the mechanical torque, or you can say that the mechanical torque or the supply torque, if it is greater than electrical torque, which is opposite to the supply torque or the mechanical torque, then only we can say that the voltage is going to get induced in the windings. Similarly, in the motor, if the supply voltage is greater than the back EMF induced, then only we can say that the motor is going to get rotated. So in a DC motor, we can say that whenever the supply voltage is greater than the induced voltage, so this induced voltage polarity is always opposite to the supply voltage polarity, because it is going to oppose the current. So therefore we can say that then only the motor is going to rotate, or simply whenever the electrical torque is greater than the load torque, then only we can say that the motor is going to get rotated. So therefore we can say that in a motor, whenever the supply voltage is greater than the back EMF, because back EMF and the supply voltage has the opposite polarity, they are going to oppose the current. So therefore then only the motor is going to get rotated. Electromechanical conversion process is a reversible process, means one machine can act as both generator and also motor. See, I have already told you, if you take a DC machine, then you can operate that machine as the DC generator, or either you can apply that machine as a DC motor. So we can say electromechanical. If you give electrical input, you can get the mechanical output, or vice versa. If you give a mechanical input, you can get the electrical output. So a given one machine can work for both process, which is called as the generator process and also for motor process. So that is the reason we call this as the reversible process. So we can say simply that this electromechanical conversion process is a reversible process. So this electromechanical conversion process is a reversible process, means one machine can act as both generator and also the motor. So therefore I have already told you, a one machine can act as both generator and motor, because the electromechanical conversion is basically a reversible process. Means simply we can say that whenever if you give electrical input, we can get the mechanical output. Similarly, if you give the mechanical input, then you can get the electrical output. Due to time varying flux in transmission line, so because of this, inductance is present but not in HVDC transmission line. So due to time varying flux in transmission line, so because of this, inductance is present but not in HVDC transmission line. See, if you take a AC transmission line, when the current is alternating in nature, so whenever the current is alternating in nature, the flux is also alternating in nature. So whenever there is a rate of change of flux, an inductance is going to get present there, which is called as the AC inductance. But in HVDC, the current is a constant, so therefore simply we can say that the flux is also constant, so there is no rate of change of flux, so there is no inductance. So therefore, due to time varying flux in transmission line, so because of this only inductance is present, but this is absent in the HVDC transmission line. So therefore we can say that whenever there is a in AC transmission line, inductance is present, but it is absent in the HVDC transmission line, because the flux is varying only in the AC transmission line but not in the DC transmission line. In early days, we got DC generator, DC motor, and DC power system and DC supply. So in the initial days, when Thomas Alva Edison was there, he was the person who invented this DC generator. So initially, in the olden days, we have the DC generator, DC motor, DC power system, or simply we can say DC supply. So based on DC only, the people are going to get power. So therefore they are going to basically generate the DC supply, and the people are going to get the DC in each and every household also. So during early days, we used to have the DC generator, DC motor, DC power system, and the DC supply. So the early days we are basically used to get the DC generators, DC motors, DC power system, and DC supply. I have already told you the total flux linkage is equal to flux per one tone into total number of tones, where phi is called as the flux per one tone and n is called the number of tones. So therefore, if you do the multiplication of n into phi, you are going to get the overall flux produced by the n number of tones, where phi is the flux produced by one individual tone and n is the number of tones are present, then lambda is equal to phi into n is called as the total flux which is produced by n number of tones, which is lambda is equal to phi into n. Then EMF induced is directly proportional to rate of change of flux linkage. So if you take lambda here, you are going to get finally with the negative sign E is equal to minus n d phi by dt, because n is a constant. So we can take it outside the differentiation. So we are going to get E is equal to minus n d phi by dt. Here minus is because with the help of the Lenz law, and this magnitude was given by the Faraday. This magnitude was given by the Faraday and this negative sign is given by Lenz law. So overall this law is the combination of both Faraday's law and also the Lenz law. So minus n, this d phi by dt I can write in another fashion, which is d phi by di into di by dt. As I have already told you, d phi by di is nothing but inductance, because inductance is nothing but which is because the flux is directly proportional to I. If you remove the proportional, the flux is equal to L into I. So L is equal to phi by I. So or d phi by di in the linear region. So therefore minus L di. So minus L di by dt. Let me assume n is equal to 1 here. Then we are going to get minus L into di by dt. So finally we can say E is equal to minus L di by dt is the overall EMF induced in a inductor inductance. So therefore E is equal to minus L di by dt. If the total flux linkage is directly proportional to current. So lambda is equal to, if you remove the proportionality constant, we have to use a symbol, the constant called as self-inductance, which is L into I. But lambda is equal to N into phi is equal to L into I. So L is equal to N phi by I. As you can see clearly, which is N phi by I is nothing but L. So minus L di by dt. So this is the overall amount of EMF induced in a inductor of coil n number of turns, which is E is equal to minus L di by dt. See, time invariant flux, conductor rotating, this we will see in the DC machines. So time invariant flux and the conductor rotating, this we will see in the DC machines. See, in DC machines, the flux is a constant, it will never rotate or it will always stationary with respect to surface. Whereas the conductors are going to get rotated, so we can say that the flux is a constant in nature, but the conductors are rotating. So we can say this, we are going to see the principle in the DC machines. I have already told you, whenever the flux is a constant with respect to time and the conductors are going to get rotated, then whatever the EMF induced in the conductors is called as the dynamically induced EMF. So therefore, the time invariant flux means constant with respect to time and the conductors are rotating. This we are going to see in the DC machines, and whatever the EMF induced in the conductors is called as the dynamically induced EMF. Whereas rotating flux and the stationary conductors, this we will see basically in the synchronous machines. I have already told you, in the synchronous machines, for higher rating machines, we are going to keep the field winding on the rotor and the armature coils on the stator. So because of the rotation of the rotor, we are going to get a rotating flux and the stationary conductors. Then we can say that whatever the EMF induced in the conductors because of this rotating flux is again called as the basically dynamically induced EMF. So therefore we can say that, and we will see this principle we are going to see basically in the synchronous machines. So therefore rotating flux and the stationary conductors, this we are going to see in the synchronous machines. Whereas flux is stationary, but it is time varying nature. It is a time varying nature, and the stationary conductors we are going to see in the transformers. So basically in the transformers, the conductors are stationary and the flux is also stationary, but it is changing with respect to time. So therefore, but here the flux is changing with respect to space, but here the flux is changing with respect to time. So therefore, simply we can say that this principle that we are going to see in the transformers, then whatever the EMF induced in the coils, it is said to be called as the statically induced EMF, because the conductors are stationary, but the flux is rotating, is changing with respect to time. So it is called as the statically induced EMF. So whenever the flux is stationary but time varying nature, the stationary conductors, then we are going to see in the transformers. Generators we can replace with AC generators but not DC motors, because they have excellent speed control techniques. See, I can say that, see, if you have these generators or AC generators, we are maximally prefer to use the AC generators. Whereas if you compare the DC motors and AC motors, we maximum try to prefer the DC motors because they have the excellent speed control techniques. Means by using the control techniques of speed control, we can get whatever the speed that we want, we can easily get it. So this is the beautiness of the DC motors. So here, if you in the terms of generators, we always try to prefer the AC generators, but not DC generators. But if in the case of motors, we try to prefer to use the DC motors rather than the AC motors because DC motors has the excellent speed control characteristics, speed control techniques. So whatever the speed that you want, you can easily get by these controlling methods. I have already told you different types of speed controlling methods of the DC motors. One is called as the armature resistance control and one is called as the free field weakening control. These things I have already explained. So therefore we can say that we can replace the DC generators by AC generators, but we can't replace the DC motors by AC motors because DC motors have the excellent speed control techniques. So these generators we can replace with AC generators but not DC motors because they have the excellent speed control techniques. See, I have already told this important concept. The Fleming right hand rule is basically applied for generator because in a right there is a R, in generator there is R in the middle here. So therefore the Fleming right hand rule is applicable for the DC generators, and I have already told you now the thumb is called as it is a motion or movement or torque, and the forefinger is going to represent the flux and the middle finger is going to represent the current or EMF. So in a DC generator, the known quantities are the flux direction and the movement of the conductors. But we don't know the direction of the current. We can get this direction of the current with the help of this right hand thumb rule. So therefore simply we can say that here this thumb is nothing but it is a mechanical torque. So always it's a mechanical torque but not the electrical torque. Electrical torque is quite opposite to the mechanical torque. The number of electrical voltage cycles induced for one rotation of one rotor conductor is equal to P by 2, and P is equal to the number of poles, it is always even number, and the number of rotations per second is equal to N by 60. I have already told this important point. Then the total number of frequencies is equal to, just do the multiplication of these two things, then P by 2 into N by 60, which is cycles per rotation into rotations per second. So rotations are going to get cancelled. Finally we are going to get cycles per second. So frequency unit is the number of cycles per 1 second, or simply we can say hertz. So therefore if you do the simplification, we are going to get N is equal to 120 F by P, where N is called as the RPM, it is number of revolutions per minute. So therefore N is called as 120 F by P. So the number of electrical voltage cycles induced in one rotation of one rotor conductor. So the number of electrical voltage cycles induced for one rotation of one rotor conductor is equal to P by 2. So if you rotate the one conductor in one revolution, the number of voltage cycles which are going to induce are called as the P by 2. And P is called as the number of poles, which is always even, and rotations per second is nothing but the number of rotations per second, which is equal to N by 60. So frequency is the multiplication of the previous two values, which is P by 2 into N by 60, which is cycles per rotation into rotations per second. The rotations which are going to get cancelled, we are going to get finally cycles per second, which is called as the frequency, or simply we can say hertz. So if we do the simplification, we are going to get N is equal to 120 F by P, where the unit of M is called as the RPM. So therefore if you rotate the one conductor in a one full cycle of one revolution, if there are P number of poles on the stator, the number of electrical voltage cycles which are induced in one conductor for one rotation is equal to P by 2, and P is called the number of poles or even number, and the rotations per second is N by 60, because N is the revolutions per minute, but if you want per second, which is N by 60 is the revolutions per second. So if the multiplication of these two things, P by 2 into N by 60, it is cycles per second and it is rotations per second. These two things are going to get cancelled, we are going to get cycles per second. It is also called as the hertz, or you can simply say that these number of cycles we are going to get per 1 second. So therefore if you do the manipulation, we are going to get N is equal to 120 F by P, where N is called as the number of revolutions of this rotor in 1 minute, which is RPM, which is 120 F by P. So for a constant frequency, by increasing the number of poles, we should decrease the speed of rotation of prime mover to get that frequency. As I have already told you, N is equal to 120 F by P. So therefore, F is equal to we can say that N is equal to 120 F by P. So for a constant frequency, if you want a constant frequency, then definitely by increase the number of poles. So we have to increase the number of poles and we should decrease the speed of rotation, because F is equal to P into N by 120. If you do the manipulation, we are going to get F is equal to P into N by 120. If you are going to increase the poles, then definitely you have to decrease the speed, then only the watt will be constant value. So therefore, for a constant frequency, by increase the number of poles, we should decrease the speed of rotation of prime mover to get that frequency, or you can do the vice versa also, which is for a constant frequency, by increase the speed of rotation and then you have decrease the number of poles to get that constant frequency. So this is the thing that you can easily get from that equation, which is called N is equal to 120 by P. So from that you can easily derive this equation. So therefore we can say that for a constant frequency, by increase the number of poles, we should decrease the speed of rotation of prime mover to get that frequency. You can do the vice versa also, which is by increasing the speed of rotation and therefore we are decreasing the number of poles, still we are going to get the product as cos of is equal to frequency. AC generator can be designed in any mode, either stationary or rotating armature, because there is no need of commutator. As I have already told you, AC generator can be designed in any mode, either stationary or the rotating armature, because there is no need of commutator. As I have already told you, in the AC generator you don't need a commutator. Only in the DC motor and the DC generator we need the commutator, otherwise we don't use the commutator. So therefore we can keep the armature coil either on the rotor or either on the stator, because we don't need the commutation process in AC generator. So as AC generator doesn't need any commutation, so we can keep the field winding, or we can say we can keep the armature winding either on the rotor or either on the stator. As I have already told you, we are going to keep the rotor winding on the rotator on the we are going to keep the armature winding on the rotor for low rating machines, but for higher rating machines we are going to keep this armature winding on the stator. These things I have already told you in the detailed manner in the previous class only. So therefore we can say that a generator can be designed in any mode, stationary or rotating armature, because there is no need of commutator. Split ring is also known as commutator. See, split ring is nothing but slip rings means it is a fixed to the windings, whereas the split ring is also called as a commutator. It is also known as the commutator. This generator is considered as AC generator with commutator. See, if you keep for AC generator, if you keep a commutator, but overall combination is called as a DC generator. These things have already told you. So therefore, the combination of AC generator plus commutator is called as a DC generator. So therefore, split ring is also called as a commutator. So the combination of the AC generator and the commutator is called as a DC generator. So therefore, split ring is also split ring. This is a split ring. So split ring is also known as a commutator, and this generator is considered as the AC generator with commutator. As I have already told you, the electrical angle is equal to mechanical angle into P by 2. So whenever the number of poles is equal to 2, then in that case always the electrical angle is equal to mechanical angle. In all the EMF equations we are going to use only the electrical angle. So therefore always you have to use the electrical angles in our formulas. In all the formulas of electrical machines we have to use only the electrical angles. So electrical angle is equal to mechanical angle into P by 2, where P is the number of poles. It is always an even number. MN is called as the magnetic neutral axis. It is always perpendicular to the net flux direction always. See, at no load, suppose if you are not going to connect any load to the DC machine, then the armature current is equal to 0, then the magnetic neutral axis and the geometrical neutral axis are going to get coincide with each other, and it is always perpendicular to the net flux. At no load, the net flux is equal to field flux, so it is perpendicular. But if you connect the load, then definitely the armature winding will have some current. So because of that, armature flux is going to get produced. So the field flux and the armature flux, they are both are going to get interact with each other. So there is a distortion in the overall flux. So the overall flux direction is going to get changed. And if you draw an axis which is perpendicular to this net flux, that is called as the MNA. So now MNA axis and the GNA axis both are quite different. There will be a small amount of angle between them. So therefore we can say that always the magnetic neutral axis is always perpendicular to the net flux direction always. Only at no load both the MNA and GNA are going to get coincide, but at the load condition MNA will never coincide with the GNA. The axis which we draw directly on the poles is called as the D axis. See, if you take a poles And if you draw an axis if you draw an axis which is passing through these poles, it is called as the d-axis. And the axis which is electrically perpendicular to d-axis is called as the q-axis. As you can see clearly here, there are two poles. So if I draw an axis which is passing through these two poles, it is called as the d-axis. And if an axis which is perpendicular to this axis is called as the electrical, it is called as the q-axis. The axis which is passing through that poles is called as the d-axis, and the axis which is electrically perpendicular to the d-axis is called as the q-axis. As we can see here, these two are two poles, so electrical angle is equal to mechanical angle if there are two poles. But general equation is equal to electrical angle is equal to mechanical angle into p by 2. So if any axis which is electrically perpendicular to d-axis is called as the q-axis. So in this case here, this is called as the q-axis and this is the d-axis. The axis which we drawn directly on the poles is called as the d-axis, and the axis which is perpendicular electrical to the d-axis is called as the q-axis. So now we are going to see this table which is very much important. So this is the quantity and this is the rate of change of flux linkage, and this is the flux linkage. It is the flux linkage and this is the rate of change of flux linkage. See along the q-axis, so this is the d-axis, and along this q-axis, if any coil which is along this q-axis, we can say the overall area, the area is maximum, so the flux can pass through this overall maximum area. See, as the area is a maximum, the flux can pass through this total area, so we can say the flux linkage is maximum, but the rate of change is 0. So we can say that if you keep any brushes across this q-axis, then the rate of change of flux linkage at this instant is 0, so no EMF is induced. So therefore always we have to keep the brushes along the MMA, because at that instant the flux linkage is maximum, but the rate of change of flux linkage is 0. So whatever the EMF induced at that brushes, whatever the EMF induced at the coils at this q-axis is always equal to 0. If you keep along d-axis, we can say if any coil which is along the d-axis, we can say that the overall area is minimum. Passing through this field. So therefore the flux linkage is minimum, but the rate of change is maximum. So this is the concept that you always need to keep in mind. So therefore along this q-axis, the flux linkage is maximum because the area is maximum, but the rate of change is 0. Whereas along the d-axis, the flux linkage is minimum, it is nearly equal to 0 also, but the rate of change is maximum. So this is the point that you always need to keep in mind. That is the reason always we keep the brushes along the q-axis. So therefore we can say that at that instant, whatever the coil which is going under the commutation, at that instant there will be EMF induced is equal to 0, so no spark we can get. So now we will discuss some important things which is called as a yoke. Yoke is nothing but it acts as a mechanical protection to the entire DC machine. So if you see a DC machine, there is a yoke. Yoke is nothing but it is a mechanical protection to the entire DC machine. It supports the poles. It is going to support the poles. It will offer flux path completion, because from the poles only there is a flux path completion. So therefore from the poles the field is going to get generated and it will pass through the yoke and it will complete the full circulation, because always the magnetic flux is a closed path. It is going to complete its path through the yoke. It is made up of good magnetic material, because the magnetic field should pass through it, so therefore it should be completely made of good magnetic material. In small machine, cast iron, and in large machine, cast fabricated steel is preferred. So in the small rating machines, we are going to use the cast iron to make the yoke, whereas in the large machines we use the cast fabricated steel is preferred to make the yoke. And always the permeability of the iron is always lesser than the permeability of the steel. So more is the permeability, more is the flux it can easily pass. So basically yokes are non-laminated. See, we never make the yokes as laminated, because yokes are always non-laminated. We are not going to laminate the yokes. So therefore we can say that yoke is nothing but it is going to act like a mechanical protection to the entire DC machine. It is going to support the poles. Basically yoke is nothing but it is going to act like a mechanical protection to the entire DC machine, and it is going to support the poles. And I have already told it is going to offer the flux path completion, and it is basically made of good magnetic material. So in the small machines we are going to make this yoke with the help of cast iron, and in the large machines we are going to use the cast fabricated steel to make this yoke. And always the permeability of the iron is very less when compared to permeability of the steel. So yokes are non-laminated in case. We are not going to laminate it. So Yokes are always non-laminated. So now we'll discuss about the poles in a DC machine. See, the pole shoe is parabolic in shape. So if you see the end of this poles, it will be like a parabola shoe. It is a parabolic shape. It is called as the pole shoe. So pole shoe is parabolic in shape to get good voltage waveform. See, because we are going to do that thing basically to get the good voltage waveform. So poles are having steel laminated to reduce eddy with 0.5 mm thick. So poles are having steel laminations to reduce the eddy. So we can say that the poles are being steelly laminated, or we can say we are going to use the steel to make the poles, but they are laminated. So poles are having steel laminations to reduce the eddy currents, with 0.5 mm thick. Electromagnet is more stronger than the permanent magnet. So electromagnet means if you own a coil on any steel or iron, that is called as the electromagnet. It is more stronger than the permanent magnet. So we can say that poles are basically, if you see the end of the pole, there will be like small parabolic shape. It is called as a pole shoe. See, we are doing this because to get the good voltage waveform. And also these poles are being laminated with the help of steel, because they are made by steel, and they are laminated because to reduce the eddy currents, and their thickness is basically 0.5 mm thick, and electromagnet is always more stronger than the permanent magnet. And if you see clearly, the yoke is always not laminated, whereas the pole is always laminated. This is the concept that you always need to keep in mind. So armature core. See, armature core means, I already told in DC machine, the armature core means the middle part. Here, steel has high permeability and good conductor. These things are just now I told you, the permeability of the steel is very higher when compared to permeability of iron, and it is also good conductor. The steel is it has high permeability, and it is also good conductor. So silicon of 3 to 4% is added to it, so that mu is same but conductivity decreases. See, the biggest property of steel is it is having the high permeability and also good conductor. But we don't need a good conductor because the eddy currents are going to get passed, so therefore losses are very higher. So we don't want eddy currents, so therefore we have to increase the resistivity of the steel. So we are going to add the silicon. So by adding the silicon, we are not going to change the permeability of the steel, but we are going to increase the resistivity. The amount of silicon that we need to add only 3 to 4%, but not more than that. If we add more than that, the overall material is going to become brittle, so it can be easily broken. So that is the reason steel is having high permeability and good conductor. So silicon of 3 to 4% is added to it, so that mu is same, but the conductivity decreases. And also laminate the armature core to prevent the eddy current losses. So basically we can say that yoke is not laminated, but the poles are laminated, and the armature core is also laminated. So this is a very important point that you always need to keep in mind. As I have already told you, this armature core is basically made of steel, and which is laminated in nature. And also steel is having the good permeability and the good conductor. So we need the permeability but not the conductor. We need to decrease the conductivity by adding a silicon of 3 to 4%. By adding a silicon of 3 to 4%, we are going to decrease the conductivity, but we are not going to change the permeability of the steel. It's a very good thing, and we can say that by increasing the resistivity or decreasing the conductivity, we are going to reduce the eddy current loss. So this is a very important point regarding the armature core. So steel has high permeability and good conductor. So silicon of 3 to 4% is added to it, so that mu is same but conductivity decreases. If you add the silicon more than this percentage, the overall material is going to become more brittle, so it can be easily broken. And also laminate the armature core to prevent the eddy current loss. So we need to laminate this armature core to prevent the eddy current loss. So now we'll discuss about the commutator. See, we have studied about the yoke, we have studied about the poles, we have studied about the armature core. I have already told you yoke is not laminated, whereas the poles are laminated, and the armature core is also laminated. So now we will discuss about the commutator. See, in the commutator, if any spark occurs on commutator, then it means the commutation is not successful. See, whatever the coil which is going under the commutation, it must not produce any spark. If it produces any spark across the commutator, we can say it is not successful commutation. If there is no spark, we can say it is a very successful commutation. So if any sparks occurs on commutator, then it means that commutation is a failure one or not successful. But if no spark occurs on the commutator, then we can say it's a very successful commutation. See, always it's a very important point that you always need to keep in mind. The number of commutator segments on commutator. The number of commutator segments on commutator is equal to number of coils on the armature core, always irrespective of type of winding. So this is a very important point. See, this is a very important point. The number of commutator segments on commutator. The number of commutator segments on commutator is equal to number of coils on the armature core, always irrespective of the type of winding. So number of commutator segments on commutator. The number of commutator segments on commutator is equal to the number of coils on the armature core, always irrespective of the type of winding. So irrespective of the type of winding, whether it is a lap winding or whether it is a wave winding, irrespective of the winding, the number of commutator segments always is equal to the number of coils on the armature core. See, whatever the number of coils in the armature core is always equal to the number of commutator segments on the commutator. The number of commutator segments on the commutator is always equal to the number of coils of the armature, irrespective of the type of winding, whether it is a lap winding or wave winding. So this is a very important point because most of the questions have been asked on this concept. So I recommend you to remember this general one, which is the number of commutator segments on commutator is equal to the number of coils present on the armature, which is independent of type of winding, whether it can be lap winding or whether it can be wave winding. So just by counting number of segments on commutator, we can tell number of coils present on the armature core. So I have already told you the number of commutator segments on commutator is always equal to the number of coils which are present on the armature core. So just by counting the number of segments on commutator, we can tell the number of coils present on the armature core. Suppose if you see a DC machine and if you see the commutator, because commutator is always visible to a human eye, coil is always outside. So if we count the number of segments on the commutator, so just by counting that, we can tell the number of coils which are present on the armature irrespective of the type of winding. So we can say that always this is a very important thing that you always need to keep it remember. The number of segments present on the commutator is always equal to the number of armature coils present on the armature. So therefore, the number of segments on the commutator is equal to the number of coils present on the armature irrespective of the type of winding. So the number of commutator segments present on the commutator is always equal to the number of coils present on the armature irrespective of the type of winding. Split comes on the brush. So whenever the split comes on the brush, one of the armature coils get short circuited. So make sure voltage across that coil at that point is 0. See, this is a very important point. I have already told you. Whenever the split comes on the brush, so whenever the split comes on the brush, one of the armature coil is going to get short circuited. Make sure voltage across that coil at that point is 0. Otherwise, you are going to get a spark. See, I have already told you whatever the coil which is undergoing the commutation. So whatever the coil which is going under the commutation, so what is going to happen basically is if the commutator segment, if the commutator segment, if it is lying on the brush, then the brush can short circuit both the brushes. Or we can say that sometimes the brush can short circuit both the commutator segments. At that instant, whatever the coil present there, it should not have any voltage, or we can say it should not have any voltage. If there is any voltage, a spark is going to get occur. So you have to make sure whatever the coil which is going under the commutation, you should have a 0 induced voltage. So whenever the split comes on the brush, one of the armature coil gets short circuited. Make sure voltage across that coil at that point is 0. As I already told you, see, across two commutator segments there is an insulator. So whenever this commutator is moving across the brushes at one instant, these two brushes are going to pass through these brushes. So therefore, if a brush is intersecting both the commutator segments, so there is a short circuit. So now a coil which is present there, it will get short circuit. So we have to make sure that at that instant the voltage across that coil should be always equal to 0. Otherwise, if it is not 0 means there is a spark is going to get occur. So always whatever the coil which is undergoing the commutation, you need to make sure that there is no voltage induced at that point in that coil. So whenever the split comes on the brush, one of the armature coil. Split is basically insulator, that insulated between the two brushes, two commutator segments. The split piece is the insulator which is present between the two commutator segments. So whenever the split comes on the brushes, one of the armature coil gets short circuited. Make sure voltage across that coil at that point is 0, otherwise you are going to get a spark. The brushes are placed on the commutator such a way that the coil gets short circuited along the MNA, which is Q axis. MNA is also called as the Q axis. Therefore, the brushes are physically placed along B axis but schematically placed on the Q axis. This concept I have already told you in a very detailed manner. So the brushes are placed on the brushes are placed on the commutator. The brushes are placed on the commutator such a way that the coil gets short circuited along the MNA. I have already told you in the Q axis. In the Q axis, the flux linkage is maximum, but the rate of change of flux linkage is 0. The EMF induced is also equal to 0. So we can say that the coil is going to get short circuited across the MNA. So therefore the brushes are physically placed along the A axis. So therefore we can say that the brushes are physically placed along the D axis but schematically placed on the Q axis. This concept I have already told you. So if you see physically, if you go into lab and if you see the basic DC machine, you can see clearly the poles we can say the brushes are basically placed along the D axis. But if you draw a paper diagram of the DC machine, you are going to show it along the Q axis. This is the only thing that is a very different view. So practically the brushes are going to place along the D axis, but schematically means if you are going to draw a paper diagram, we are going to show the brushes along the Q axis. This is a very important point. So therefore we can say that, see, I have already told you the coil which is going under the commutation should have 0 induced voltage. It is possible only when the coil is along the MNA axis, or you can say Q axis. At that point the voltage linkage is maximum, but the rate of change of voltage is minimum, so EMF induced is 0. So therefore we can say that simply the brushes are placed along the D axis, but the coil, then only we can say that the coil which is going under the commutation will have a 0 induced EMF there. So practically the brushes are placed along the D axis, while schematically they are placed along the Q axis. The brushes are placed on the commutator. The brushes are placed on the commutator such a way that the coil gets short circuited along the MNA Q axis. Therefore the brushes are physically placed along the D axis but schematically placed on the Q axis. This concept I have already told you. See, always we are going to keep the brushes on the commutator segments. So one important point is I have already told you, if the coil is along the MNA axis or Q axis, the maximum flux linkage will happen, but the rate of change of flux linkage is 0. The EMF induced will be 0. So if the coil is along the MNA axis, the EMF induced at the distance is equal to 0. So whatever the EMF is equal to 0. So now we need to do the short circuit. Then we have to keep the brushes along the D axis. Then only we can make the short circuit the brushes. So simply we can say that physically the brushes are placed along the D axis, but schematically if you draw a paper diagram, they are placed along the Q axis. So two conductors means one tone. I have already told you one tone means we have two conductors. So for Z conductors we have Z by 2 tones. So therefore for two conductors we have one tone, and for Z conductor if you do the simplification we are going to get Z by 2 tones. It's a very simple simplification because two conductors means one tone. So Z conductor means number of tones. You can easily do cross multiplication and then you get the result which is Z by 2 tone. So one tone is nothing but single turn coil. So one tone is also called as the single turn coil because a coil of single turn is called as the single turn coil. The winding makes cooling of machine more efficient. See, distributed winding makes cooling of machine more effective. These things I have already told you. The advantage of using the distributed winding. I have already told you distributed winding means if you keep the coil sides in different slots, it is said to be distributed winding. But if you keep all the coil sides in a one slot, it is said to be concentric winding. I have already given the detailed comparison of the concentric winding and the distributed winding. So distributed winding is going to give you it is going to make the cooling of the machine more effective than the concentric winding. So distributed winding makes cooling of the machine more effective than the concentric winding, and the output voltage is nearly constant. So if you use the distributed winding, we can simply say that the output voltage is nearly constant. The output voltage is nearly constant with the help of this distributed winding, and it makes a good balance and gives more output speed. It is also going to make a good balance of the winding, and it gives the more output speed. And the reactance is minimum due to making separate coils than single coil. So reactance is minimum due to making separate coils than single one. So these are the some of the advantages of using the distributed winding when compared to concentric winding. So distributed winding makes the cooling of machine more effective, and output voltage is nearly constant, and it is going to make the good balance and gives the more output speed. And the reactance is minimum because due to making separate coils than single one. So distributed winding makes cooling of machine more effective than the concentric winding, and the output voltage is nearly constant, and it makes good balance and gives more output speed. And reactance is minimum due to making separate coils than single one. So these are the advantages of the distributed winding when compared to concentric winding. So distributed winding makes cooling of machine more effective than concentric winding, and the output voltage is nearly constant and makes good balance and gives more output speed. And the reactance is minimum due to making separate coils than single one. The distance between the two coil sides of a coil is called the coil span. The distance between the two coil sides of a coil is called the coil span. I have already told you the coil span is nothing but if a given coil, so for a given coil there are two coil sides, the distance between the two coil sides of a given coil is called as the coil span. So if the coil span is equal to pole pitch, it is said to be a full pitch winding. If the coil span is less than pole pitch, it is said to be a short pitch winding. If the coil span is greater than full pitch, it is called as the over pitch winding. These concepts I have already told in the synchronous machine. So therefore, the distance between the two coil sides of a coil is called the coil span, which is basically express the number of conductors or slots. We are going to represent with the help of the number of conductors or slots. The distance between the two coil sides of a coil is called the coil span, which is express the number of conductors or slots. The distance between the two coil sides of a coil is called the coil span, which is express the number of conductors or slots. So these things I have already told you. The distance between the two coil sides of a given coil is called the coil span. It is basically expressed in number of conductors or slots. Pole pitch is defined as center to center distance between two adjacent poles, expressed as number of slots or number of conductors per pole. Pole pitch is defined as center to center distance between two adjacent poles, expressed as number of slots or number of conductors per pole. See, pole pitch is nothing but it is defined as the center to center distance between the two adjacent poles, expressed as number of slots or number of conductors per pole. So basically pole pitch is nothing but it is going to defined as the center to center distance between the two adjacent poles, expressed as number of slots or number of conductors per pole. These things I have already told you. The pole pitch means it is basically defined as the center to center distance between the two adjacent poles, which is expressed in number of slots or number of conductors per pole. The pole pitch formula is 180 degree by the pole pitch means the number of slots per pole. So pole pitch means the total number of slots by total number of poles. So we can say that simply the pole pitch is defined as the center to center distance between the two adjacent poles, which is expressed in the terms of number of slots or number of conductors per pole. The formula is pole pitch is equal to total number of slots by total number of poles. Then we are going to get a ratio which is called as the number of slots which are for one pole, the number of slots which are defined for one pole, the number of slots which are defined for one pole is called as the pole pitch, or simply the center to center distance between the two adjacent poles which are defined expressed in terms of number of slots or conductors per pole. The coil span is made exactly equal to pole pitch, but it is called as the full pitch coil, which produces maximum voltage in it. These things I have already told you. Whenever the coil span is equal to pole pitch, it is called as the full pitch winding. Then you are going to get a maximum voltage in it. But whenever the coil span is less than pole pitch, it is called as the short pitch winding. And whenever the coil pitch is greater than full pitch, than the pole pitch, it is called as the over pitch winding. These concepts also I have already told you. So if the coil span is made exactly equal to pole pitch, then it is called as a full pitch winding or full pitch coil, which is going to produce the maximum voltage in it. Whereas if the coil span is less than the pole pitch, it is called as the short pitch winding. And whenever the coil span is greater than pole pitch, it is called as the over pitch winding. Usually DC machines windings are full pitch type, which coil with the coil span exactly 180 degree electrical. These things I have already told you. So general DC machine windings are full pitched winding, full pitch type winding with the coil span exactly equal to 180 degree electrical. So I have already told you the electrical degree of pole pitch is nothing but 180 degree. I have already told this one. The electrical angle of pole pitch is nothing but it is equal to 180 degree. So therefore simply we can say in a DC machines whatever the winding we prefer, it is basically full pitch winding. So simply we can say the electrical angle of full pitch winding is equal to 180 degree. So generally DC machine windings are full pitch type with the coil span exactly 180 degree electrical. So therefore the coil span, whatever the coil span and because the coil span is equal to pole pitch in the case of DC machine, the winding is said to be full pitch winding. So the electrical angle is nothing but 180 degree. Electrical angle between two ends in full pitch winding is 180 degree. These things I have already told you. Therefore the electrical angle between the two ends in a full pitch winding is equal to 180 degree. The electrical angle between the two ends in a full pitch winding is equal to 180 degree. This concept also I have already told you. So therefore the electrical angle between the two ends in a full pitch winding is always equal to 180 degree. So always in a full pitch winding the electrical angle is equal to 180 degree and the coil span is also equal to 180 degree because a full pitch winding the coil span is equal to pole pitch. So therefore the electrical angle of full pitch winding and the coil span is always equal to 180 degree. So generally the DC machine windings are full pitch type with the coil span exactly 180 degree electrical and the electrical angle between the two ends in full pitch winding is 180 degree. In single layer winding, one coil set is placed in one slot. See, in single layer winding, one coil set is placed in one slot and the number of slots is equal to number of coil sets. It's a very important thing that you always need to keep remember. So therefore, in a single layer winding, one coil set is placed in one slot. So therefore, in a single layer winding, one coil set is placed in one slot and the number of slots is equal to number of coil sets that we can see easily. So therefore, suppose if you take an armature, see, let me give you some details regarding the armature. Suppose in armature there are number of slots and there are number of coils. So in a single layer winding, one coil set is placed in one slot. So therefore the number of slots is equal to number of coil sets. So therefore in a single layer winding, one coil set is placed in one slot. So therefore the number of slots is equal to total number of coil sets. Suppose there are 30 coils. So 30 coils means each coil has 2 coil sets. So into 2, so you are going to get 60 coil sets. So add a single layer winding. So 60 coil sets means in each slot we are going to keep 1 coil set. So we are going to get 60 slots. So 60 slots means I already told you the number of coils is always equal to number of commutator segments irrespective of the type of winding. As you can see clearly that here I already told you the number of commutator segments is always equal to number of coils. Here we are going to get 30 coils. So therefore the number of commutator segments is also equal to 30 because I already told you the number of commutator segments is always equal to the number of coils present on the armature irrespective of the type of winding. As there are 30 coils, so we are going to get 30 commutator segments. So this is a very important point. In a single layer winding, one coil set we are going to keep in one slot. So therefore the total number of slots is equal to total number of coil sets. Here we take a small example. There are 30 coils. 30 coils means each coil has 1 coil set. So each coil has 2 coil sets. So 30 into 2 is 60 coil sets. So 60 coil sets means 1 coil set is in 1 slot. So 60 coil sets means 60 slots. I have already told you the number of commutator segments on the commutator is always equal to number of coils present on the armature. As there are 30 coils, so we are going to get 30 commutator segments. Similarly, it is in the case of single layer winding. In standard double layer winding, see, now in case of standard double layer winding, 2 coil sets are placed in one slot. In double layer winding, we are going to keep 2 coil sets in one slot. So 2 coil sets we are going to keep in one slot. And then you will see what is going to happen. The number of slots is equal to, the number of slots is equal to now number of coils, because two coil sets in one slot. So we are going to get the number of coils is equal to number of slots here is equal to number of computer segments. I have already told you the number of computer segments is always equal to the number of coils which are present on the number of coils present on the armature. So this is a very important point that you always need to keep remember. So therefore the number of slots is equal to number of coil sets is equal to number of computer segments in case of the double layer winding. Let me take a small example. So 30 coil sets. 30 coils means suppose there are 30 coils. So for one coil there are 2 slots. So for one coil there are 2 coil sets. So 30 into 2 is 60 coil sets. So I have already told you 2 coil sets placed in one slot. So 2 coil sets in one slot. So 60 coil sets in 30 slots. So we are going to get 30 slots. So you can see clearly 60 coil sets in 30 slots because 2 coil sets in one slot. So 60 coil sets we are going to get 30 slots. So 30 slots we are going to keep. As I have already told you, the number of coils on the armature coil is always equal to number of coils. We can say that I have already told you the number of coils in the armature is always equal to number of commutator segments on commutator. So as there are 30 coils, we are going to get 30 commutator segments. So this is a very important point that you always need to understand regarding the single layer winding and the double layer winding. So we can see clearly, let me repeat this example in the single layer winding. Suppose there are 30 coils. So each coil has 2 coil sets. So 30 coils means we are going to get 60 coil sets. And I already told in the single layer winding, one coil set is placed in one slot. So as there are 60 coil sets, we are going to get 60 slots. So then I have already told you, in respect to the type of winding, the number of commutator segments on the commutator is always equal to number of coils, which is equal to 30. So 30 commutator segments. Suppose in case of double layer winding, you will see 30 coils means one coil has 2 coil sets. So therefore 30 into 2 is nothing but which is 60 coil sets. Then I have already told you in double layer winding, 2 coil sets are placed in one slot. So 60 coil sets are going to present in 30 slots. 30 slots is equal to, I have already told you, the number of commutator segments on commutator is always equal to the number of coils present on the armature. It is irrespective of the type of winding. So therefore it is a 30 commutator segments.
So now we are going to discuss about the concentric winding. So basically concentric winding is used in the transformers, DC machine poles and the silent pole alternators. So we are going to basically use this type of concentric winding. It is used in the transformers. See, and also on the DC machine poles and the silent pole poles also. And the silent pole alternators also we are going to use this concentric winding. So we can say simply that there are 2 types of windings. One is called as the concentric winding and the other one is called as the distributed winding. So basically we are going to basically use this concentric type of winding. So this concentric type of winding is basically used in the transformers and also DC machine poles and also the silent pole alternators. Basically in that the field winding. In the field winding we are going to use this concentric winding. So we are going to use this concentric winding in the transformers, DC machine poles and also in the silent pole alternators, especially in the field winding. Then comes the distributed winding. It is of 2 types. They are called as the open winding and the closed winding. So distributed winding is of 2 types. One is called as the open winding and the other is called as the closed winding. So distributed winding is of 2 types. One is called as the open winding and the closed winding. So now we'll discuss these two windings in a very detailed manner. So open winding is used in AC windings, which is like star to delta or synchronous machine or induction machine or 3-phase winding. So this open winding is basically used in the AC winding, which is like star to delta, and also in the synchronous machine like induction machine and the 3-phase winding. So you can see clearly that the open winding is basically used in the examples like star to delta. In synchronous machine, the armature winding which is placed on the stator, here we are going to use this open winding, and also this induction machine. In the induction machine also we are going to use this winding which is on the stator and also on the rotor, which is of split phase machine, and the 3-phase winding also. This open winding is used in basically AC winding like star to delta, synchronous machine and also in the induction machine of the 3-phase winding. So closed winding is of 2 types. They are grammering and drum. So grammering and drum, both these are used in armature windings. So both these are basically used in the armature windings.
So we can say that the distributed winding is of two types. One is called as the open winding and the other one is called as the closed winding. So open winding is basically used in the AC windings like star to delta, synchronous machine, induction machine and the three-phase winding. Whereas the closed winding is of two types. They are called as the Gramme ring and the drum. Both these are used in the armature windings. So both these types are going to use in the armature winding. Again, the drum winding is of again three types. They are called as the lap winding, wave winding and the frog leg winding. So drum winding is again classified into three types. They are called as the lap winding, wave winding and the frog leg winding. So frog leg winding is made of both lap winding and wave winding mixture. So frog leg winding is basically a mixture of both the lap winding and also the wave winding. So all these are used in the armature windings. So all these are basically used in the armature windings. So finally I can say that windings are of two types. One is called the concentric winding and the other one is called as the distributed winding. Again, distributed winding is again classified into two types. One is called as open winding and the other is called as the closed winding. Again, the closed winding is again classified into two types. They are called as the Gramme ring winding and the drum winding. Again, the drum winding is classified into three types. One is called as the lap winding, wave winding and the frog leg winding. And the frog leg winding is a mixture of both the lap winding and the wave winding mixture. So all this basically used in the armature winding itself. So you can see clearly here windings I have given each and everything in a detailed manner. So windings are classified into two types. One is called as the concentric winding and the distributed winding. Again, the distributed winding is of two types. One is called as the open winding and the closed winding. Again, the closed winding is again classified into two types. One is called as the Gramme ring and also the drum type. Again, drum type is classified into three types. One is called as the lap type, wave type and the frog leg type. So frog leg type is basically a combination of both lap and wave. So this is the configuration of the windings. So windings are classified into two types, concentrated winding and the distributed winding. And the distributed winding is classified into two types, open winding and the closed winding. So again, closed winding is again classified into two types. One is called the Gramme ring and the drum. Again, drum is classified into three types. One is called as the lap winding, wave winding and the frog leg winding. So now we'll discuss another concept. Here YB is called as the back pitch. Back pitch means the span of coil at the back end. It is the span of the coil at the back end. And YF is called as the front pitch, or simply we can say the span of the coil at the front end. So YB is called as the back pitch or span of coil at the back end, and YF is called as the front pitch, the span of coil at the front end. And YR is called as the winding pitch or the resultant pitch. So YR is called as the resultant winding pitch or the resultant pitch. Distance between the start of two consecutive coils. It is the distance between the start of two consecutive coils. Suppose YR is equal to YB minus YF. If YB is greater than YF, then YR is said to be positive. So it is said to be progressive winding, means the winding is going to move in the forward direction. If suppose YB is less than YF, then YR is equal to negative. It is called as a retrogressive winding. So this is a very important point that you always need to keep in your mind. So YB is called as the back pitch. We can say simply the span of coil at the back end, and YF is called as the front pitch. We can say the span of coil at the front end, and YR is called as the winding pitch or the resultant pitch. It is the distance between the start of two consecutive coils. So YR is equal to YB minus YF. If YB is greater than YF, then we say YR is equal to positive. It is called as the progressive winding, means the winding is going to move in the forward direction. If suppose YB is less than YF, then YR is equal to negative. Then simply we can say retrogressive winding, means the winding is going to move in the backward direction. So this is a very important point that you always need to keep remembering, because there are a lot of questions have been asked on this concept. So therefore YB is called as the back pitch or span of coil at the back end, and YF is called as the front pitch, the span of coil at the front end, and YR is called as the winding pitch or resultant pitch. It is the distance between the start of two successive coils. So YR is equal to YB minus YF. If YB is greater than YF, then YR is a positive. It is said to be progressive winding, means the winding is going to go in the forward direction. If YB is less than YF, means YR is equal to negative. The winding is going to move in the backward direction. It is called as a retrogressive winding. YC is equal to plus or minus M. It is called as the commutator pitch. The number of commutator segments between two successive coils. So this is a very important formula, which is YC is equal to plus or minus M. It is called as the commutator pitch. Here the number of commutator segments between the two successive coils. The number of commutator segments between the two successive coils is equal to YC is equal to plus or minus M. So YC is called as the commutator pitch. It is the distance, the number of commutator segments between the two successive coils is called as the commutator pitch. The number of commutator segments between the two successive coils is called as the commutator pitch. Number of commutator segments between the two successive coils is called as the commutator pitch, which is Yc equal plus or minus m. Here positive for the progressive winding present. We have to use the plus for the if the winding is a progressive winding, and we have to use the minus whenever the retrogressive winding is used. So this is a very important point that you always need to keep in mind. So therefore, here plus we have to use whenever the winding is progressive winding, and we have to use the negative whenever the retrogressive winding is used. So positive for progressive winding present and negative for the retrogressive winding is present, and m is equal to 1 for the simplex winding and m is equal to 2 for the duplex winding. So we have to use m is equal to 1 for the simplex winding, and we have to use m is equal to 2 for duplex winding. So this is the thing that you always need to keep in mind. So Yc is equal to plus or minus m. Yc is equal to the commutator pitch. We can say the number of commutator segments between the two successive coils is called as the commutator pitch. The number of commutator segments between the two successive coils is called as the commutator pitch. So plus we have to use whenever the winding is a progressive winding, and we have to use minus whenever there is a retrogressive winding is present, and m is equal to 1 for the simplex winding and m is equal to 2 for the duplex winding. See, for lap winding, Yb and Yf must be both odd always. See, this is a very important point for lap winding. So for lap winding, Yb and Yf must be both odd always. See, Yb and Yf are always odd numbers. These are all always odd numbers for the lap winding. So for lap winding, Yb and Yf must be both odd always. So for lap winding, Yb and Yf should be always odd. For simplex lap and progressive winding, so for lap winding, I have already told you, for lap winding means Yb and Yf should be always odd values. So for lap winding, Yb and Yf should be always odd values. Suppose for simplex lap and progressive winding, simplex means m is equal to 1, and lap winding means Yb and Yf are both odd always, and it's a progressive winding means Yb is greater than Yf. So these are the things that you can get from this equation, which is simplex lap. See, for simplex lap and progressive winding, simplex means m is equal to 1, and lap winding means Yb and Yf are always odd values, and progressive means Yb is greater than Yf. So these are the things that you can get from this one, which is for simplex lap and progressive winding, simplex means m is equal to 1, lap means always Yb and Yf are always odd values, and progressive means Yb is greater than Yf. The number of parallel paths depends on the number of poles in the lap winding. I have already told you in the lap winding, the number of parallel paths in the armature is equal to number of poles. The number of parallel paths depend upon the number of poles in the lap winding. Generally, it is preferred for the high current and the low voltage ratings, because more the number of parallel paths, more is the current rating and less is the voltage. So therefore, higher current and lower voltage ratings. Due to large number of parallel paths, any magnetic asymmetry will create unbalance in the voltage between the parallel paths and produce a high circulating current to interfere with the commutation process. To bypass the circulating currents, equalizer rings are connected at the back ends, tapped to equal equipotential coils. So this is a very important point. So basically, the number of parallel paths depends upon the number of poles in the lap winding. Generally, it is preferred for high current and low voltage ratings. Due to large number of parallel paths, any magnetic asymmetry will create unbalance in the voltage between the parallel paths and produce a high circulating current to interfere with the commutation process. To bypass the circulating currents, equalizer rings are connected at the back ends, so tapped to equipotential coils. See, this is a basic important point I already told you. In a lap winding, the number of parallel paths is equal to number of poles. So more the number of parallel paths means the poles are very higher. So because of the more number of parallel paths, the current rating is higher and the voltage rating is very less. So all the parallel paths should have the same voltage ratings, but due to some magnetic asymmetry, we may get different voltage in the different parallel paths. So we can say unbalance. We are going to create a unbalance in the voltage between the parallel paths. So whenever there is an unbalanced voltage across the parallel paths, a huge amount of circulating currents are going to present. So therefore we can say that the commutation is going to get failure. So we have to bypass these currents. So we have to bypass the circulating currents with the help of equalizer rings. So we have to connect these equalizer rings at the equipotential coils. So whatever these bypass currents, whatever the circulating currents, they can pass through these equalizer rings, and we can protect the basically the windings from huge amount of circulating currents with the help of these equalizer rings. So these are connected at the back end of the equipotential coils. The number of parallel paths depends upon the number of poles in the lap winding. Generally, it is preferred for high current and low voltage ratings. Due to large number of parallel paths, any magnetic asymmetry will create unbalance in the voltage between the parallel paths and produce a high circulating current. To interfere with the commutation process, to bypass the circulating currents, equalizer rings are connected at the back ends tapped to equipotential coils. So because of that, because of equalizer rings, we are going to remove the circulating currents because they are going to produce whenever there is a magnetic asymmetry. Number of equalizer rings is equal to number of coils in armature by P by 2. So this is a basic formula. The number of coils in armature by P by 2. I have already told you the number of commutator segments is equal to number of armature coils on the rotor. The number of commutator segments is equal to number of armature coils irrespective of the type of winding that we are going to use. Whether it is singular winding or whether it is double layer winding or whether it is a lap winding or whether it is a wave winding. Irrespective of the type of windings, I have already told this point. So number of equalizer rings is equal to number of coils on the armature by P by 2. So this is a very important formula. The number of equalizer rings is equal to number of coils in armature by P by 2. So when number of parallel path increases in lap winding, for high current applications, always equalizer rings must be connected in order to save from circulating currents. I have already told this point. So when number of parallel path increases in lap winding, for high current applications, always equalizer rings must be connected in order to save from circulating currents. Because for lap winding means the large number of parallel paths is equal to number of poles. So the current rating increases, the voltage rating decreases. So all the parallel paths should have same amount of voltage. But due to some magnetic asymmetry, there may be a case we can get unparalleled, means the voltages are not equal to same because of the parallel path. So because of this, the circulating currents are going to get produced. So therefore we can say huge amount of losses. So therefore commutation may get failure. So to remove this one, we are going to keep these equalizer rings across the equipotential coils. So therefore, whenever there is a asymmetry, the circulating currents can pass through these equalizer rings and it can save the windings from these circulating currents. So therefore conversion now can become very good process. So therefore, when number of parallel path increases in lap winding, for high current applications, always equalizer rings must be connected in order to save from circulating currents. And the number of equalizer rings is equal to the number of coils in armature by the total number of poles by 2. So YB and YF must be both odd. Then only winding on the armature is perfectly symmetrical. I have already told you YB and YF should be always odd in nature. Then only we can say that whatever the winding on the armature is perfectly symmetrical. So YB and YF must be both odd. Then only winding on the armature is perfectly symmetrical. So YB and YF should be always odd in values. Then only we can say that whatever the winding that you are going to use on the armature is perfectly symmetrical. So YB and YF must be both odd. Then only winding on the armature is perfectly symmetrical. So YB and YF must be both odd. Then only the winding on the armature is perfectly symmetrical. Empirical formula will always not give perfect solution. So empirical formula will always not give perfect solution. If YB and YF, if you get even, then always choose nearest odd values for both. See, whatever the empirical formulas I have already told you, the empirical formulas that I have already told you, those will never give you the perfect solution. So if YB and YF, if you got some even values, then try to choose the odd values which are near for both them. So because YB and YF should be always both, irrespective of the winding. So whatever the empirical formula, they will never give you the correct answer. So you have to choose the YB and YF to a odd values always. So this is the very important point that you always need to keep remembering this one. So therefore, the empirical formula will always not give perfect solution. The empirical formula will always not give perfect solution. If YB and YF, if you got even, then always choose the nearest odd values for both. Because YB and YF should be always odd, then only we can say that they will be always having the symmetrical configuration. So whatever the empirical formula, it will never give you correct solution. Sometimes you may get even values. Then what you have to do is basically choose the odd values which are near to them. So empirical formula will always not give you perfect solution. If YB and YF, if you get even, then always choose nearest odd values for both. See, for lap winding, I have already told you the number of parallel paths is equal to number of poles. It is for the simplex lap winding. Simplex means we can say that there are no, the simplex means we can say n is equal to 1. But for multiplex lap winding, A is equal to P into M. So this is a very important formula that you always have to remember. See, always number of parallel paths is equal to number of poles into M, where M is called as the multiplex lap finding, or we can say multiplicity. So therefore it is for the multiplex lap finding. M is equal to 1 for simplex, M is equal to 2 for duplex, M is equal to 3 for triplex, M is equal to 4 for quadruple. So this is a point that you always have to remember. So A is equal to P into M. This is a very general formula. The number of parallel paths in lap finding, in multiplex lap finding, is equal to P into M. So A is equal to P into M means A is called as the number of parallel paths in multiplex lap finding, which is equal to A is equal to P into M, where P is the number of poles and M is the multiplicity of the winding. M is equal to 1 for simplex, M is equal to 2 for duplex, M is equal to 3 for triplex, and M is equal to 4 for quadruple. So for wave winding, A is equal to 2. Here basically 2 into M. So it is also here for wave winding, A is equal to 2 into M for the multiplex wave winding. So this is an important formula here. 2 into M. The number of parallel paths is equal to 2 times of M. Here M is called as the multiplicity wave winding. So for multiplex wave winding, the number of parallel paths is equal to 2 into M. M is for simplex, M is equal to 2 for duplex, M is equal to 3 for triplex, M is equal to 4 for quadruple. So for simplex, so generally we are going to take the simplex wave winding. For simplex wave winding, A is equal to 2. So only 2 branches are needed, also called as the series winding. So wave winding is also called as the series winding, and it has for simplex wave winding. So for simplex wave winding, A is equal to 2 because M is equal to 1. So only 2 branches are needed. Only 2 brushes are needed because I have already told you the number of brushes is equal to number of parallel paths. The number of brushes is always equal to number of parallel paths. So this is a very important point. So therefore the number of brushes is equal to number of parallel paths. The number of brushes is always equal to number of parallel paths. So this is a very important point. So the number of brushes is equal to number of parallel paths. So therefore for wave winding, A is equal to, for simplex wave winding, A is equal to 2. So only 2 brushes are needed. So also called as the series winding. So now these are the new formulas, which is Ya is equal to Yb plus Yf by 2 is equal to Z plus or minus 2 by P. It is the equation 1, and Yb is equal to Yf, the second equation. So these are the equations for the wave winding. So Yb plus Yf by 2 is equal to Z plus or minus 2 by P, and Yb is equal to Yf. It is a second equation. So use these 2 equations in the wave winding to get the value of Yb and Yf. So these are the equations that you have to choose, that you have to use for the wave winding. So these are the equations that you always have to choose for the wave winding, which is Yb plus Yf by 2 is equal to Z plus or minus 2 by P, and Yb is equal to Yf. So these are the 2 equations that you have to choose for the wave winding. So use these 2 equations in the wave winding to get the value of Yb and Yf. So these are the 2 equations that you have to choose. Yb plus Yf by 2 is equal to Z plus or minus 2 by P, and Yb is equal to Yf. So these are the 2 equations that you have to choose, and you have to solve these 2 equations to get the value of Yb and Yf. Here these are the equations only for the wave winding. So use these 2 equations in the wave winding to get the value of Yb and Yf. So in some set of data, the average pitch may not be an integer. So these 2 equations in the wave winding to get the value of Yb and Yf. So you have to solve these 2 equations to get the value of Yb and Yf in the wave winding. So in some set of data, the average pitch may not be an integer. So an adjustment may be done to get an integer value by choosing the proper jet from the given jet, which leads to mechanical unbalance. In order to maintain it, dummy coils or dead coils used, which are not connected to anything. So basically in some set of data, the average pitch may not be an integer. So it may be some fraction parts. So an adjustment may be done to get an integer value by choosing proper jet from the given jet. So from the given jet, we have to choose the proper value of jet. So always the average value should be always an integer. So which leads to mechanical unbalance. In order to maintain it, dummy coils or dead coils used, which are not connected to anything. So because of this, there will be an unbalance in the coils, in the armature. So definitely you have to use some extra dummy coils, which are used only to make the mechanical balance. See, this is not going to connect to anything. Just it is going to only provide the mechanical balance to the armature or the rotor. So only it is going to provide some balance. It is not going to connect anything, because we are choosing only a particular value of jet from the overall jet to get the average value as an integer. So the remaining jet are also present. So because of that, there is unbalance So if you want to make the balance of the armature, definitely you have to use some extra dummy coils. So therefore, the rotor is at balance condition, but it will never provide anything. It is not connected to anything. So therefore, in some set of data, the average pitch may not be an integer. So an adjustment may be done to get an integer value by choosing proper jet from the given jet, which leads to mechanical unbalance. In order to maintain it, dummy coils or tip coils used which are not connected to anything. A is equal to 2 for simplex wave winding and A is equal to 2 into M for multiplex wave winding. So this is a very important formula. A is equal to 2 for the simplex wave winding and A is equal to 2 into M for the multiplex wave winding. So finally I can say that here this is the formula for the multiplex wave winding. So finally I can say that A is equal to M into P for multiplex lap winding and A is equal to 2 into M for multiplex wave winding. So A is equal to P into M for multiplex lap winding and A is equal to 2 into M for the multiplex wave winding. So this is the concept that you always have to remember for your lifetime. As there are only two paths in a simplex wave, no need of equalizer rings because any unbalance will become balanced automatically. So as there are only two paths in a simplex wave, so no need of equalizer rings because any unbalance will become balanced automatically. So in a wave winding, there are only two parallel paths, so automatically any unbalance can become balanced automatically. So we never use the equalizer rings in a wave winding. So only in the lap winding we use the equalizer rings, but not in the wave winding. So only in the lap winding we are going to use the equalizer rings, but not in the wave winding. Yeah, any unbalance can become balanced automatically in the wave winding. So in the wave winding, Yc is equal to number of coils plus or minus 1 by P by 2. So Yc is equal to number of coils plus or minus 1 by P by 2. So this is the formula for the in wave winding. So in wave winding, Yc is equal to, Yc is equal to number of coils plus or minus 1 by P by 2. So Yc is called as the commutator pitch, or we can say the number of commutator segments between the two successive coils is equal to number of coils plus or minus 1 by P by 2. So this is the formula that you always have to remember. So Yc is called as the commutator pitch, is the number of commutator segments between the two successive coils is equal to number of coils plus or minus 1 by P by 2. So this is the formula that you have to use. You have to find the value of Yc for the wave winding. So with less number of parallel paths, the problems will also be less. So wave winding is preferred. So with less number of parallel paths, the problems will also be less. So wave winding is always preferred. So we can say that if the number of parallel paths are less, the problems associated with it is also are less. So that is why wave winding is always preferred rather than the lap winding. So with less number of parallel paths, the problems will be also very less. So wave winding is preferred. So in DC machine up to 50 kilowatt, we use wave winding, no need of equalizer rings. I have already told you for lower rating machines, which we try to use the wave winding. Up to 50 kilowatt, we try to use the wave winding because it has less number of parallel paths, so less number of problems are associated. And I have already told you equalizer rings are associated with only lap winding but not with wave winding. So no equalizer rings are required for these machines. So in DC machines up to 50 kilowatt, we use the wave winding because it has less number of parallel paths, means the less number of problems have been associated. So no need of any extra equalizer rings. For higher power rating like current high, we use lap winding, and the power rating increases, its current rating increases. So we prefer the lap winding. If you want a higher power ratings like current rating high, then definitely we use the lap winding. As the current rating increases, the power rating increases. So here we are going to prefer the lap winding. So whenever the lap winding is going to get occur, we always have to use the equalizer rings. So for higher power rating like current high, definitely we have to use the lap winding because as the power rating increases, the current rating increases. So we prefer the lap winding. In the lap winding, we always use the equalizer rings. Armature core and pole shoe have the iron loss in a DC machine. See, I have already told you armature core. See, I have already told you yoke is not laminated, but poles are laminated, and also the armature core is laminated. So armature core and pole shoe have the iron loss in a DC machine. That is the reason I have already told you one important point. See, always poles have been laminated, and the armature core is also laminated. So definitely they will have the iron losses. So armature core and also will have the iron losses in a DC machine.